Okay. Well, welcome everyone to the 2021 Gauge Sage DAS workshop. My name is Casey Adderholt. I work at the Incorporated Research Institutions for Seismology. And I'd like to introduce Eileen Martin, who's been our fearless leader in this organization of this workshop. Ariel Lelouch, who is also joining us. Sorry, I'm not seeing everybody's faces, but you'll hear from him later. Rachel Hatch, Dante Frate, Bob Woodward, Herb Wang, Scott Tyler. Am I missing anyone? I'm so sorry, I don't have my notes in front of me. Anyways, it's been wonderful to work with these people to bring this workshop together. And we're very excited to have everyone. So just some quick Zoom etiquette. There's a few quirks with the Pathable platform, as I'm sure you'll realize, but make sure your real name is showing up in the participant list. You can rename yourself if it is not. Please mute your microphone, keeping background noise to a minimum when you're not speaking. And when we're working in these large sessions, you can turn your video off just to save on bandwidth for some participants. But please turn them on when we're in like breakout sessions so that we can have more interaction. You can limit your distractions if you'd like. That's probably a good idea for everyone. There's also closed captions available on the Zoom toolbar. So if you have any issues getting those started, just let one of us know. We did run into some issues with the virtual platform chat box. There was an update to Pathable recently, and so we don't mind if you use that chat box in the Pathable event page, but if you'd like to use the one in the Zoom page, that's fine too. So we'll keep an eye on both chat boxes. But if you don't see a chat box on the website, that's probably a quirk of the update. Right, we'd like to encourage a culture of effective collaboration throughout the Gauge Sage workshop. And so these are some guidelines to follow in that: treat others with respect and consideration, value a diversity of views and opinions, be considerate, inclusive, respectful, and collaborative, communicate openly with respect for others, critiquing the ideas rather than the individuals. And this group of us comes from a diversity of institutions around the world, from colleges to research institutes and more. So remember that realities will vary. Believe others if they describe situations that seem different than your experience, and support each other in brainstorming solutions based on different realities. So if you have any issues, please do communicate with any of the leaders. Oh, this is, of course, yeah, especially important for these breakout groups later on when we're having more interactive discussion. But please keep this also in mind in your questions or really more of a comment. All right, so we'll go ahead and get started a little bit late, I'm sure. But thanks so much for being here. This is the first part of our agenda, so we'll go ahead and get started with Eileen Martin. Would you like to?
All right, thanks, Casey. Yeah. There we go. Let me get that screen sharing working. All right, so with these workshops, this is being coordinated through the DAS Research Coordination Network, which many of you may be members of, or maybe you've never heard of it, and maybe this is your first exposure to distributed acoustic sensing. So we wanted to start off with just a sort of 15-minute short introduction to distributed acoustic sensing, just to make sure that everyone has some shared background knowledge and that this event is really accessible to those who are new to working with DAS. So we're going to look at some basics. So what is distributed acoustic sensing? Why do we use DAS, which I call it DAS for short. Some people say DAS. It's up to you what you want, how you want to pronounce it. We'll see, what does DAS really measure, and how do we get and share DAS data? So a simple model of DAS is that we have an optical interrogator unit with a laser, and it's going to probe a fiber optic cable And it's going to send this light pulse down the cable. And as that light pulse encounters various impurities in the cable, we're going to have optical backscattering. And it's called Rayleigh optical backscattering. And we're going to measure some time series of the photons that are returning. Now, this isn't exactly the principle behind every distributed acoustic sensing system, but it's one of the basic principles for some implementations. So once we get that light returning to us, we know that 2 times the time that it took that light to return to the interrogator unit times the speed of light in fiber is going to tell us what's that distance to where that light was backscattered. And if I happen to have a vibration source at a particular point, and I ping that fiber many times repeatedly, well, as that vibration changes, the time it takes is going to adjust a little bit as that fiber expands and contracts. And so that means that I can tell where along the fiber I'm getting those vibrations and approximate how strong they are. Okay, so this means that we're going to get a bunch of these little time series as we ping our fiber multiple times, and we're going to look at where there are changes. It's denoted here with that blue circle and those purple circles. And the distance over which we're kind of measuring the average of those changes is what we call a gauge length. So we're actually measuring what's the average extension or compression of a segment of fiber that we're going to refer to as this gauge length. So a typical gauge length might be maybe 1 meter or 10 meters or 20 meters, depending on the system that you're working with. And then we also chop up that signal, that's time series, into little segments. And depending on how long a time it is between how we chop that up, that corresponds to a distance over which we start a new, what we call a channel. And so that channel length is different than our gauge length, but that channel length basically says, what's the distance between one sensor location and the next sensor's beginning of its location? There are some limitations. So we need to make sure our laser pulse can go all the way along the fiber and back. So if we have a really long fiber, that gives us some limits on how fast we can measure our seismic velocity or our seismic profile there. We also have some noise that's optical noise, and doing this conversion from optics into getting some kind of strain or strain rate measurement, depending on the system. So there are some limits there. There's also limits in the installation on whether we have good coupling of our fiber optic cable to the ground where we're really trying to measure the vibrations. So we may not actually be getting the true strain or strain rate of the ground. We may actually be getting some approximation of it with some energy loss due to whatever the coupling issues might be for our cable to the ground. Okay, but at least we're able to get really fine sampling in space and in time. So over on the right, you see an example of 600 channels worth of data. We've got 4 meters per channel. So that means a new sensor location every 4 meters. And this was recorded on the Stanford campus. And this is just 10 seconds of data. And we can see a lot of detail in here. We've got busy roads, we've got a car driving by, there's a construction site that had a lot of pops going off. So we get to see just unprecedented detail in a lot of new situations. So, okay, we're starting to think about, okay, if we want to have that detail, that's one reason we might use DAS, but there's actually a lot of other reasons that we might use DAS. So in the oil and gas industry over the past decade or so, DAS has really caught on for lowering costs for doing geophysical monitoring. So especially things like doing microseismic monitoring throughout production, having full coverage of a well, that's really useful for them. Being able to take a fiber optic and leave it in place in a well for repeatable time lapse or 4D monitoring of either geomechanical or fluid changes, that's really important for them. So getting that time lapse reproducibility is a big advantage. And there's also some extensions to try and get better response for things like reflection seismology in that space. And for the same reasons that the energy industry has really latched onto using DAS, we might also think about this for a wider range of problems in engineering geophysics or geotechnical engineering, in glaciology, in marine geophysics, urban seismology, a lot of different situations. So the benefits that we're seeing from the oil and gas are also benefits to us as often more research type scientists. So we see dense sensor spacing, we can cover long distances, which means tons of sensors at relatively low labor to install and maintain. We can go into new locations where you could easily fit a fiber optic cable, but maybe you wouldn't have been easily able to go and install maybe a node or some traditional seismometer. We get really broadband response. We can also leave our sensors in place for really long periods of time. And we don't have to be attaching our interrogator unit to our cable all the time. We can plug it in for a little while, then stop measuring and come back to the same cable later after leaving it in place for a while. And again, having really low labor acquisition is important for us. So like I mentioned, on the Stanford Fiber Optic Seismic Observatory, we could see really a lot of details throughout the campus. So in these urban settings, it's really catching on. We can also see those differences in the frequency domain, especially tied to sort of anthropogenic changes. Like here you see day and night trends throughout a week. We can also detect small, weak earthquakes. Because we have so many channels, this allows us to do array processing that's really simple. And we can come up with a variety of different sort of quantitative metrics that are smaller to maybe put into our earthquake detection methods. We can also look at farther away large teleseismic events and use strain measurements of those, along with our traditional seismic networks. And we can even do things like ambient noise interferometry, like this example, which was at the Stanford array, and we can get different types of wave modes out of that. And especially in these areas where we're trying to bring DAS and passive seismic into areas where people live and work, we have to be able to detect anthropogenic noises and remove those. And so we're starting to see a growing role of machine learning in distributed acoustic sensing for things like denoising and other types of processing as well. We're also seeing this grow in use in permafrost thaw monitoring. So here are several examples of arrays that were set up by Jonathan Aho Franklin and Anna Wagner and collaborators, where we were monitoring permafrost thaw in a little section that was heated up in Fairbanks, Alaska. And so it's very easy to leave the fiber optic in place from 1 year's experiment and then add even more sensors later. You just splice them together when you have time to expand your experiment, and it's relatively easy to expand your experiment or to just leave the fibers in place for a year between your monitoring experiments. And this is even being used in glaciology increasingly. And so a recent experiment led by Fabian Walter and Andreas Fichtner was to deploy about 10 kilometers of fiber optic cable on the Rhone Glacier in Switzerland. Collect about a month's worth of data, and you can see a lot of details here. A lot of what we're seeing here is wind noise, but as we've actually dug into this, we can see a lot of small seismic events going off. And these events are just visible on small portions of the array, but because we have such extensive coverage and really fine spacing, DAS allows us to be able to detect many more of these events than what had ever been previously possible with more sparse node arrays. All right, so, okay, maybe at this point you're thinking, wow, DAS sounds great, but I don't really know what it's measuring. You know, let's get a little bit more into what is the measurement. And as you're working with the data, this is important in understanding how you'll process that data. So what we're really recording oftentimes is axial strain rate or axial strain, depending on the system, it'll be one or the other. So imagine that I've got my cable and it's broken up into little segments. And this is just broken up in the sense of how we're processing that laser light, not in any physical sense of actually breaking up the fiber. And if it's relaxed, all right, we've got a little gauge length as one section of the fiber. But if we have some tension, we're going to have that gauge length increase. And so that tension is our axial strain. Or if we're looking at the time derivative of that, we're going to be looking at our strain rate in that axial direction along the fiber. Okay, so we can think about that as basically the x derivative of the particle velocity in the x direction at a particular location if our fiber is oriented in the x direction. And what's really nice about this is also that we can compare that directly to the difference of two geophones that are side by side. So if I've got two geophones that are a gauge length apart and I take their difference of their components in line with the fiber, that's actually equivalent to what we're measuring as our average strain rate throughout that gauge length. So we can do these kinds of comparisons, and you can see some nice examples of this in the Brady Hot Springs data and some other experiments out there. But strain rate is a tensor quantity. And we're mostly just looking at this axial strain rate that's a single component in one direction. But this does mean that when we're having sources come in from different directions, we're actually having to apply a couple of rotation matrices, which means that our responses are a little bit different. So if I have longitudinal waves on, let's say, a typical geophone that's measuring particle velocity, I'm going to have this kind of a sensor response. But if I'm working with DAS, I'm going to get a little bit more extreme directional sensitivity. And if I'm working with transverse waves, I actually am going to emphasize 4 different lobes of regions of sensitivity if I'm working with DAS, as opposed to 2 lobes with the traditional geophones. So we do have quite different interpretation of some of our data, especially if we have that kind of shear motion. But we do see that these patterns show up in our real P-wave data. So tests by the group at Shell have confirmed that, for instance, we had a cosine squared responsive sensitivity for our P waves, which are longitudinal. All right, so we have a little understanding of what DAS is measuring, what DAS is, why we use it. And you may be wondering, well, how do I get my hands on some DAS data? And Ariel Lelouch is going to show you a bit more about this soon. But right now, if you want to get some open DAS data, you can go to the OpenEI initiative through the Department of Energy. They also have within this the geothermal data repository, which is actually hosted on Amazon's S3 cloud servers. There are some data sets that are just up on GitHub with links to Google Drive folders. Researchers have really had to hack together solutions so that we can share data, because we don't have a sort of common community repository for the DAS data at this point in time, but hopefully that's coming in the near future. Some groups are just mailing hard drives between each other, and some are able to host their data on university data archives with their library resources or things like that. So here's a collection of just 8 sets of data, and I think that this is all being recorded, so hopefully you can kind of pause if you're interested in any of these to look at the details of where you find these. But we're starting to get a lot more data that's being shared, a variety of things ranging from near surface experiments all the way to unconventional wells, offshore experiments, things like that. So hopefully you can get your hands dirty pretty quickly now. In the coming year, I know there are a lot more plans to release more DAS data sets. So hopefully this list will be too long to fit on a single slide soon. But one of the issues when you get your DAS data is that it's often very large scale. So typically we're looking at hundreds of thousands, millions of points per second collected by an experiment. And these experiments may run for days, weeks, years sometimes. Just taking a small collection of these experiments ranging from low data rates to high data rates, you can see that just a little collection of these experiments added up to about the same quantity of data as the entire IRIS DMC in just a 4 or 5 year period. And so you do have to be really smart about your processing and those data workflows to not get overwhelmed with the amounts. A lot of times this means there's hard drives, a lot of hard drives to share and store, or people are using kind of local archive storage. But this isn't great for our scientific community. And so looking forward, hopefully some of the solutions will be things like reducing data quantities with things like lossy compression, which is something my group works on, doing algorithmic advances for efficient array processing, which we're also working on, and hopefully getting some public archives expanded with maybe cloud provider resources or things like that. One thing you can do at this point, if you're already working with DAS data, is to share the code that you have. If it's efficient, if it's good at managing large amounts of data, think about joining our DAS RCN GitHub organization and linking your code over there so that it's easy for people to discover that and to share resources with each other. Just send me an email if you want to join that with your GitHub username. All right, so hopefully you've got a little better sense of what DAS is, how we use it, and hopefully you're jazzed up for the rest of the workshop. I showed a bunch of little examples that had a lot of collaborators and funding resources, so I'll just show this to make sure they're acknowledged. And thank you very much for your time and attention.
Thank you, Eileen. We're just a little bit behind now, so I'm Herb, and I'm going to moderate the remaining 3 talks in this session. One of the issues that you'll face when you're establishing a DAS array is locating distance along the fiber with a geographic point. And so our next speaker, Tori Biondi, will talk about tap testing using moving vehicles.
Thank you, Herb. Can you see the slides okay? I hope
Yes.
so. Okay, awesome. So let's get started so that we stay on time. So yeah, as Herb said, like one of the key steps once you deployed your system, the DAS system, as Eileen clearly explained, it's to geolocate the position of those channels recording the data. And sometimes it's easy, sometimes it's not that easy. And you will see here actually an example where we mapped 100 kilometers of cables recorded using 2 DAS systems in the Long Valley caldera. So, and the idea is simple, like when you have a short cable, it's easy. You can just go around and basically just tap on the system or jump around or with just an hammer hit and record the position of the hammer where you basically hit the hammer on the ground. But when you have a pretty long cable like this, actually like here we have channel, and this is more or less corresponds to 50 kilometers of distance. And this is time. This is 1 hour data, more or less, in the Long Valley caldera. And you can see here we have a highway section. In fact, you'd see a lot of traffic. Here it's a side road, this part. And basically from this position onward, it becomes basically just a dirt road. And in fact, it's not that busy. And it's easy in a sense to map, as you will later see. But the idea is that can we use a moving vehicle track with a GPS device to geolocate the position of the cable? And of course you can, as long as you can distinguish your vehicle. But it's not that hard when you have a good section of the cable where you don't have much traffic, as you will later see. So, in fact, that's exactly what I was saying. Like, can we use this signal to map the DAS system channel? And how do we do it actually when we go into the field? In deploying the system, it takes not that much time actually, like especially if you use telecommunication fibers that have already been deployed by a telecommunication company. And in fact, in this case, we can go in the field and deploy and do the tap test in 1 day. And here you can see just the approximate location of the fiber that we are going to try to geolocate. And in fact, in the field, it's very useful to have this kind of data because you will know where to drive around with your car. Another thing that actually we are using currently like different system, and especially we are currently using OptaSense recording devices. And one nice feature of their system, at least, it's the fact that we can have a real-time view of the data if you have internet connection. In fact, Ethan and I, we were driving around. He was driving, I was guiding him, and I was looking in real time the data to make sure that basically just to QC that the signal that we were producing was valid and it could be used for geolocating the car. And the bigger, the better. Of course, ideally you would like to have an 18-wheeler, but I guess you cannot go everywhere. Actually, like some section of the cables were off-road in some kind of, not nasty, but tricky situation. But anyway, if you have like a good vehicle like this one, you can really go everywhere, and it's pretty big, so it makes a lot of noise or seismic noise. So basically the idea is kind of simple in a sense, but it's crucial. Like if this step is not done properly, everything else is going to break down. And especially like you will see an example of how to use, for instance, this position to evaluate some velocity models using Econol equation, as you will later see in the presentation. But basically, like the idea is that you have your fiber location or approximate location by a telecommunication company, and you would like to combine this information with a GPS track of the vehicle and the DAS raw data, as you can see. Basically, you combine these 3 information to get the channel position, geolocation of the channels of the position of the system. And effectively, like the steps are pretty simple, but basically like I will explain later, but basically you convert your GPS position as function of time and distance moved along the cable. And in fact, here you can see that it's almost aligned, but not. In fact, there are a few steps that have to be taken here. Here we are showing basically just the envelope of the signal between 0.25 and 2 hertz. And you can see that basically the car generated noise, it's pretty clear in this kind of plot. But basically the idea is that on telecommunication fiber, sometimes they have loops, basically area where the cable goes into a manhole and it's looped around. Those areas are bad because usually they're badly coupled and they don't record good energy. And you will see exactly what I mean by that on an earthquake. And basically the next step, once you identify the bad channels, let's call them like this, you want to align the GPS data with the DAS data, as you will later see. And the idea is actually somewhat simple, like you're not allowed to shift in time this distance as function of time, because the time of the data is fixed by the GPS time, and the same goes with the GPS measure of the car, right? So the only thing you can do is just to shift up and down or left and right, depending how you turn this axis when you want to co-register, as you can see here, where this line it's pretty well aligned with the generated noise of the car. Once this is aligned, you can basically transform the position at a given time at a given channel into the position of the channel, geolocation position of the channel. So let's give a little bit more sense to it. Just how do we map the channels? We take our data and we take our GPS measurement, basically latitude and longitude as function of time of the car. The idea is that you transform latitude and longitude into a distance, of course. It's easy, basically like how long you drive for. And by knowing the channel position or channel spacing of the DAS system, this is kind of preset. You set that on the console of any DAS system. You can transform basically like this distance into some channel number. Of course, like as I said, you're allowed to shift this number as a function of whatever origin of the channel axis you want. You will see what I mean by that again. But basically, like this is the only thing you can do. Again, like the time, if the DAS system is GPS synchronized, the time in the DAS data and the time of the GPS cannot be moved. Of course, that's actually kind of crucial in this kind of test. And again, like you take your data, you shift your GPS tracked vehicle. Once you align the two, as you will later see, you can basically assign the latitude and longitude of the car at a given time to the DAS channel where you recorded the energy. And this one, it's a kind of efficient because basically like if you drive along the cable, very close to the cable, and you drive maybe for 10 kilometers, you can basically map 10 kilometers of cable in one go. It takes no time. And as I said, basically like you go in the field, you deploy the system, you do the tap test, and the next day you already have the geolocation with this kind of approach for very long cables. Actually, right now we have 50 kilometers and we are actually increasing the range to 100 kilometers. So the first step, as I said, is to remove the bad channel. And the best way to do that, actually, like we created some kind of GUI to do it, it's to look at earthquakes. You can use traffic. Traffic, it's good as well. But like when you have a pretty good earthquake, like this one, where you can see the P wave and the S wave onset, like recognizing like a loophole or like just a manhole or a loop in the system, it's obvious, as you can see here. In fact, you can zoom in and you can clearly see where you have basically like bad coupling or basically bad channels that you would like to remove. In fact, you can basically identify them, remove them, make sure that the two phases between the two sections of the cable align. And you do this for the entire cable. This process doesn't take much, especially if you have clear signal like this one, and you basically remove all the bad channels. And now you have a pretty continuous signal, as you can see here. Now, as I said, we have two systems recording data. We actually did the tap test in the same day, but in two steps, if you may. We actually first drove and performed the calibration of the south system, and then we drove north from basically in the Long Valley caldera. This is basically the I-395 highway. It's mostly along that highway, these two cables. As I said, like, let's try to map those section of the cable. Like this is basically the data. Here you're going to see basically the geolocation of the cable. This is just to have a sense of the energy of each channel. Again, like the first part is to remove the bad channels, the red one. You remove them, you have a much better continuity of the signal. You then plot your GPS position as function of distance, if you may. Basically, like here you have basically channel position or channel number, and this is time. Again, you're not allowed to shift up and down this curve, but only left and right, as I said before. You find that shift, as I said, For instance, you can clearly see that this is some kind of car generated noise. And actually you can see that this pattern, it's very, very close resembling this one. And in fact, actually, if you shift them, now you're able to say, oh, okay, the car at that time, it was at that position, and it's now you can basically assign for each channel and each time the position of the car. And you can do that. And again, here we're almost mapping 10 kilometers of cable, as you can see here. Basically, like the channel distance was 10 meters. And so basically we're almost 10 kilometers. So you do this, and this is just a zoom in, and you can now assign in your system, like for each channel, you can say whether a channel is good or bad. And also you can assign the geolocation of each channel, as you can see here. Now, the next step is to verify whether your calibration was correct or not. And one way to do it is just to basically take the GPS track vehicle position and map it to the closest channel that you mapped. And you do that, and you start looking around if whenever the car was close to the cable, you can see a generated noise by the car. And you can see that this is just one section of the cable where it's pretty clear that the car was correctly placed. And the same here, especially when you go back and forth between on the road, on the same road. But here we're going south, going north, and north again, basically. And we track the vehicle pretty well. And this is another section of the cable again. Like if you move back and forth along the cable, this is just a quality or like a QC step that is pretty useful. And this actually like is just a plot of the cable after geolocation. You can actually put in Google Maps or Google Earth and look around where your recording system and actually put the numbers of your channels. And this is basically the Long Valley Caldera. This is the South system recording data. This is Lake Crowley. This is Mono Lake. And basically we have the other system going north and recording data. Overall, from here to this position, we have basically covered 90 kilometers of cable. And we record quite a bit of data. We desample them because we don't need very high resolution. Actually, we are going to mostly look at seismological application, and you will see one of them actually later in this presentation. And for instance, like here, you can see that we recorded data for 6 months. It's still recording. These two systems are still recording. We have data up to now, basically since last November. And we have more or less, as you can see, in 6 months, we have 60 terabytes of data for each system. So as I said, like once you have the geolocation, you can really do quantitative analysis of the data. And one of them, for instance, is just to perform some travel time modeling for now. We're going to do inversion later on in the future. That's kind of the ultimate goal. But for now, let's just compare the travel time modeling using the Econol equation, the equation here. And this is just some of the earthquakes that have been occurred in this area. And this is the 2DAS system recording the data. Again, like let's look at an earthquake here. Using Econol equation, having a velocity model, you can basically compute the travel time. Basically, this is just a travel time maps of the velocity of the travel time cube. And let's compare 3 models actually. Like now that we have the geolocation of the cable and we record data and record the earthquakes, we can actually evaluate whether the onset predicted by a velocity model is good or not. And we're going to compute travel times on the Flinders model. It's a model published in 2018. The SCAC CVM 3D model, it's a model of the area constructed by the SCAC community. And another 1D model, again, by SCAC. And we're going to compare these 3 models to evaluate the quality of the velocity model by comparing the observed onset of the P and S wave with the predicted one. Let's consider an earthquake here. And basically, like what you can see here is the fact that Flinders model under predicts, and it seems that the CVM 3D model is pretty accurate, as you can see here. There are still like some mismatch, especially in the S wave, as you can see here and here. But overall, it's not a bad model, basically. And this can be done only if you have like accurate geolocation.
Atari, you have about 2 minutes.
Yep, I'm almost done. Yep. This is another earthquake. Same conclusion. The CVM model is pretty accurate if you compare these 3 curves. The 1D, it's basically arriving too early. The CVM 3D is good. And the Flinders model, it's too late in a sense. But this one, it's a good way of measuring basically the quality of a velocity model of an area once you geolocate the cable. So yeah, let's conclude. Basically, like, as I said, accurate geolocation of any DAS system channel, it's crucial for any subsequent step, especially if you want to do any kind of inversion or quantitative analysis of the system. And this is kind of tricky when you have like a pretty big or large system, such as the ones that we had. Here we had to map 100 kilometers of cable almost. And using GPS tracked vehicles, it was a great way because basically like in just one day, we could deploy the system and measure the position of the channels in a very accurate way. And I think basically we came down to an accuracy of basically 2 meters. And of course, you verify the accuracy of the model or the system by basically looking if the car was generating noise, as I said. And again, like now, I just showed that the fact that we can employ this measurement or this quantitative position of the cable to perform basically assess the accuracy of velocity models. Anyway, we would like to thank OptaSense for their support, and actually we thank Martin Karenbach, Viktor Yartsev, and Vlad Botganov for their help. And that's it. Thank you.
Thank you, Tori. Very efficient. There's one quick question from Good Jin. Does your workflow assume that the cable locations are correct and that only the channel number that is fiber distance needs to be corrected?
Yeah, exactly. That's exactly right. Basically, like the idea is that you need to have a sense of where the cable is. And if you don't have any road on which, like even if it's a dirt road, we actually like went like really into the woods, if you may. But basically, like you need to know more or less an approximate location of the cable so that you can drive around on top of it. The closer you drive on top of the cable, the more accurate you get your position, of course. Usually, like we rely on section of the cable where we can really see clear signal generated by the car. And then we interpolate. But there are very few spots where you cannot drive on top of the cable length. And by the way, like depending on the application, if it's just seismological application, the wavelengths are so large that if you go down to a 5 meter accuracy of the position, that's good enough. If you need higher resolution, then maybe like you need something else, or you need to, you know, go and refine the position of the cable if you need to do that. It depends on the application. For our goal, considering the scale of the system, this was the fastest way. And we did it like many times. Actually, I think we did it already for 6-7 systems in this way.
Okay, thank you. So let's move on to our next practical aspect. So now let's say you've collected 44 terabytes of data in a couple of weeks. What do you do with it? Ariel Alouche will describe the basics of DAS processing and a code demonstration. Ariel?
Yeah, so thanks, Herb. So far in this workshop, we talked a little bit about what DAS is, what can we expect in terms of measurements, data, resolution, things like that. And then it also showed us a cool way of locating the channels, which is obviously a very challenging part in any DAS experiment. So logically, the next thing you would do in real life workflow would be looking at your data, looking at your measurements. So these can be recorded earthquakes, these can be active seismic sources, ambient noise, whatever your interests are. But this is not something that's usually discussed in workshops, right? People don't usually say, well, then I loaded the data and plotted it. And that's why I'm here. It's going to be maybe a slightly unconventional talk. You can see it's going to be me sharing my screen and not a presentation. And the idea is to give you, again, a very basic example or guideline of how you would go about handling DAS data. So we'll start with some basic visualization, QC, a little bit of data processing, filtering, things like that. And the reasons we thought when we planned this workshop, and I'm sure Eileen, when she originally designed this this Jupyter notebook, is that transitioning to DAS can be, I think, a little bit overwhelming. Personally, I think there are two reasons. The first is that just the sheer volume of data, as Herb mentioned, you acquired 100 terabytes of data. Now, how'd you get started? But also the fact that you have to start thinking in terms of arrays. For example, if you're coming from seismology, you might be more used to thinking about point sensors. and then going on from a few tens or a few hundreds of channels to 10,000 might need a little bit of a paradigm shift. The second difficulty, I think, is that DAS data is not as well organized, or maybe not as standardized as, for example, again, seismology. You can go to the IRIS website, download seismographs from all over the world with perfect information about the location, the orientation, the instrument response, and so forth. With DAS data, I'm sure we'll get there in a few years. As Eileen mentioned, there are many initiatives and many people working towards this direction. But for now, when you're working with that data, with DAS data, it's a little bit more like in the nitty-gritty. You have to find some auxiliary information and reports, do some more kind of integration, and it's not like you get everything pre-prepared and or almost pre-prepared and ready to roll. So after this long introduction, I'm going to be using the Brady Hot Springs geothermal data. The DAS data were acquired by the Porotomo team. It's been a very prolific experiment. You can see this is a nice picture taken by Dante Frata. Lots of references. This data set has been extensively studied, and there's still papers being published about it recently, even though it was acquired in 2016. And hopefully for us, everything is accessible online. Eileen mentioned it's hosted on AWS. Of course, we will post this link so you can go back to it when you have more time, like browse through the data, and of course recreate this Jupyter notebook. It's Python based, and play with it a little bit, kind of get a feeling. Ideally, if we had more time, we would do it live, and everyone would kind of follow the same script, but we're only limited to 15 or 20 minutes, so you'll just have to bear with me sharing my screen. So as I mentioned, Python is very popular, and I'm guessing most of you are using it anyway. So we're going to follow that. Using some basic packages, that's probably what you will need. We use NumPy and SciPy like everyone else. ObsPy has some nice features that for data loading, filtering, formats, etc., and then some helper functions that we'll use along the way. Here we're using the Google Colab environment, which is pretty neat because it comes with some pre-installed stuff. But basically, you just need to install these packages before we get started. So I already did it. I just installed ObsPy, which is not a part of the Google Colab like standard distribution. And the first thing we're going to do is we're going to look at the array geometry. So, right, Ettore showed us one way of doing it. In the Brady Hot Springs, it was probably done with tap testing, which basically means people going with hammers and hitting the ground until they are located on the fiber. And if you go to this link, which we will download immediately, you will see what a geometry looks like. I hope you can see the right tab. Not sure. Anyway.
Yes, yes, we do.
Yeah. Okay, cool. Sorry. So this is basically a very simple table showing the channel number and X, Y, Z in UTM coordinates. So as I mentioned, right, it's a little bit nitty gritty. First channels are empty. You can see you also have negative channels because the way the fiber system is kind of set up. First channel is number 30. You can see, well, X, Y, Z coordinates. It's very nice. And then you have a bunch of channels until you get to the end. And then again, kind of empty channels. So we only have, well, not only, but we have 8,620 something channels for which we have the geometry. So we're going to load that long CSV file. Again, that's another package we need. We do that, and we're going to look now at a file that contains a seismic source. It's a vibrosize source, and if you come from exploration seismology, I'm sure you're very familiar with this type of source. It's basically a huge vibrating truck that can send all sorts of special pulses into the ground. It's not just like one big hit. It kind of sweeps around and generates a signal with a specific signature into the earth, and that's something that's very useful for exploration and seismic surveys in general. So let's look at one of these vibrosize shots. Again, you can follow the links. Originally, for example, locations are given in lat long, and you convert them to UTM. It's the type of things you have to do when you work with DAS data, but I warned you beforehand. So we have the source X and Y, and the first thing we're going to do is just plot the distance between the source and every DAS channel. So you can see we have like 8,000 and something DAS channels, and the distance between the source and each fiber location goes between 50 meters and 900 meters. So at the first glance, this looks a little bit tricky. I mean, it seems like a complicated geometry. So let's actually plot the fiber locations, and you can see that it is indeed a pretty complicated geometry. So we have the source here is the black circle, and the fiber locations. This is a map view, so in X and Y. You can see the first channel is somewhere here. That's channel number 1. And then you can see the fiber goes through all sorts of kind of a maze pattern all the way to channel 8,000. So we have that. So we're finally ready to look at data. So again, thanks to the Porotomo initiative, all these data are available online. I already downloaded it, and we're going to load these data that are in a SegWi format. Again, if you're coming from seismic exploration, it's something very standard. Otherwise, you can just read it with OpSpy. So we're going to just read this data and making sure that we have the right size. When you load the data, you get all sorts of parameters from the headers of the data. For example, like the number of the sampling rate, the number of samples, so give you the length of the file, et cetera, et cetera. So just to double check, we have 8,621 entries. If you remember that the geometry table, that's exactly the number of so-called live channels that we had. So indeed, everything seems reasonable. And again, the Porotomo team cut the data to only contain the meaningful channels. We don't have the dead channels that sometimes show up. I mean, when you record the data, the way the optical system works is sometimes you have kind of fake channels after the end of the actual fiber, and they are completely useless and need to be discarded. But here it's already been done for us. So let's look at one fiber channel. I just randomly chose channel 2000, and this is what it looks like. It's about 30 seconds of data. So you can see it starts with nothing, then we have this strong signal, then a quiet period, and then the next signal. This is actually the second VibroSci sweep. I'm guessing it's in the same location because it would take the truck too much time to move between points. But this is what you get for a single channel. Now, the problem is with DAS data, and I mentioned the difference kind of between this and seismology in the beginning, is you cannot look at 8,000 channels like this side by side, right? I mean, it would be impossible, and my computer would crash, and it would be very embarrassing. So instead, we're going to use a different type of plots that's very common for DAS and generally for kind of array-based processing. We're going to do a raster plot, meaning we're going to show one axis is going to be the time, the other is going to be the channel number, and the color is going to be the amplitude. So we define this function here. Again, when you have time later, you can look at how it did it. It's basically just showing an image. And this is what it looks like, such a plot of the same file that we discussed. So you have the channel number, it goes from 0 to 8,000 and something, 30 seconds of data. We can see these kind of like the full sweep and then the beginning of the next one. And here we can see that the energy is dominant in certain parts of the array, and some certain other parts are more quiet. We'll talk a little bit in later about why this happens. But this is what 8,000 channels over 30 seconds look like. And this is, I think this is about 1 gigabyte of data, just to give you a notion. Another cool thing we can do is we can plot some snapshots of the data in time. So instead of showing all times and all channels, we're going to freeze time, in this case at 3.5 seconds, and show the amplitude of the recorded strain rate as a function of spatial distance. So you can see the imprint of the fiber geometry. You can see in which portions things are stronger and in which they are weaker. We even built a widget to show how this changes with time. So very early on, and if you remember the source, let me go back to it. The source does not really start at time 0 in this case. This is just like 30 seconds of data. So at 1 second, you basically have nothing or just very weak signal. When we move forward, we start seeing the signal getting stronger. The source is somewhere here. And you can see as a result that fiber positions that are farther away get weaker signal, which makes sense, right? This is geometrical spreading. And we can keep moving forward. then things start to get weaker. This has to do with the source, which is actually a sweep signal that has the lower frequencies towards the end. And as you know, lower frequencies tend to attenuate faster. Therefore, for the low frequencies, here, for example, they reach the more distant parts of the array. For the higher frequencies, like here, they are more confined to closer to the source. And at some point, things are dying off until we get to the next sweep starting.
2 minutes now.
Oh, wow. Whoa. Okay. I'll speed it up. One thing that is interesting to think about is the effect of sensor orientation. And Eileen mentioned the fact that DAS measures strain or strain rate, but it is along the direction of the fiber. So if you're looking, for example, at this set of 1,000 channels, you can see that there are a lot of directions being sampled. And as a result, recorded data in this kind of section is going to widely vary in terms of amplitude. So amplitude can vary for multiple reasons. It can be the coupling of the fiber to the ground, which for now we assume uniform, but it doesn't have to be true. It of course depends on distance, and the further you are, the weaker the signal, but it also depends on the fiber direction. If you think about surface waves, you're going to be more sensitive to waves coming parallel to your fiber than those coming perpendicular. So really quickly, because we're running out of time, we can also look at the spectrum of recorded signals. We just took one channel, something, do the FFT and plot the amplitude. We can see that the energy kind of is centered between, I don't know, 5 and 80 hertz, something like that. We can do it for all channels at the same time, showing us a spectrogram of each individual channel. So you can see the stronger areas, those were the stronger channels that we saw earlier, and you can see more accurately maybe that the frequency content is between 5 and 80 hertz. And one cool thing that I added to this, notebook that Eileen made, is trying to remove the source signature. If you go through the reports from the Brady Hot Springs, you can find actually the pulse design. So the actual pulse that the trucks in the field used to generate the seismic source. And you can actually do a cross correlation between the recorded data and the known source. And this way you're kind of collapsing the data to something that's closer than a spike. It's not perfect. It actually leads a cloud or wavelet. But anyway, the point is, this is what the original data looks like, kind of like continuous and very wiggly. And after you do this type of correlation, you can start seeing something that looks more like seismic data. So it's much more centered in time, and you don't get like 20 seconds of information. And when you're at this point, you're basically ready to start working on seismic processing as if it was an array that is at least similar to a conventional survey. So yeah, that's it. Herb said no time, so no time.
Okay, thank you very much, Ariel. And that's a great segue to our next speaker, Jack Muir, who's finishing his PhD at Caltech. And he's going to talk about wave field-based evaluation of DAS instrument response and array design. Jack?
Sure, thanks, Herb. So yes, as Herb mentioned, I'm going to be talking about using wave fields to evaluate DAS instrument response, and also talking a little bit about array design. Full disclosure, it's currently 2 a.m. where I am in Australia, so if I say anything weird, it's probably because I'm only half awake. So please make sure that I answer any questions that you have before I leave, if I say anything strange. Can you see my screen properly?
Yes.
Okay, great. So this is work as part of my PhD with Shogwen at the Caltech Cypher Lab. So the idea from this is that in general, beyond DAS, handling large and heterogeneous data volumes is a major challenge of 21st century seismology. So we have this object, which is a seismic wave field, which is a 3D object or potentially a 4D
Jack,
object.
I'm so
Yes.
sorry to interrupt, but I think we are seeing your first slide only. So I think we aren't on the right window if you have switched slides.
Yeah, let me
Just want to check that. So sorry to interrupt, and thanks for being here at 2 a.m.
It says bring it. Let me stop and then restart.
Okay, thanks. Sorry, just didn't want to get too far in.
Yeah, for sure.
I think it was just a matter of it wasn't showing all the windows. Yeah, that looks good.
It works now. Okay, great.
Yep, looks great. Thanks so much.
Okay, so yeah, the seismic wave field is a 3 or potentially 4D object. So that's 2 or 3 spatial dimensions plus time. And we've had these major logistical efforts that have enabled very dense sampling of the wave field, which has allowed quasi 3D or in some cases even quasi 4D measurements. So we have things like the US array where we rolled lots of broadband stations across America and looked at long wavelength quasi 3D measurements. Obviously, all these weren't active simultaneously, but that's the idea. And at shorter scales, we've had things like the Long Beach geophone array experiment, where we can see the seismic wave field being recorded in quasi 3D at a shorter wavelength. But fundamentally, the data representation when we are recording the data is still in effectively an N by 1D measurement. We've talked about this, Ariel talked about this a bit before, where essentially we're recording a bunch of time series and then we have to somehow interpret them in the form of an array. And this is especially true for irregular or heterogeneous arrays. So when we have something that's very dense and relatively regularly sampled, like this Long Beach array, we can just plot it and see that we have the wave field going across. But if we have an irregularly distributed array, so the station spacing is not quite as regular as this, or we have different sources of data, for instance, DAS data, then it's harder to interpret it in terms of a single unified wave field object, which is really what we want to understand in seismology. DAS in particular offers special challenges for wavefield representation. So it has some features like channel spacing is very dense in one direction, but it's irregular and sparse in other dimensions. We're accessing the strain wave field rather than the displacement wave field, and you can take time periods of those, which then complicates both the theory and the practice of what we're sensing. And often we can only access so-called dark fiber, so pre-laid fiber, not specially designed for a particular experiment, which is not necessarily designed for array performance. So this is the bottom of a figure from one of Chopin's review papers, showing the Brady Porotoro experiment, which is what I'm going to be using in this talk as well, which is a specially designed layout, but they have lots of nodes and sort of complicated array geometry that gives you some aerial coverage. But then we also have these examples of dark fibers. So the Stanford DAS array, this is Fossa line and the Goldstone array, where we have essentially, as I said, very dense station sampling along the cable, but very sparse sampling across the cable. So these present interesting challenges for thinking about wavefield representations. What is it about the wavefield that we need to understand in order to represent it accurately? So if we think about the seismic wave equation, what it really depends on is both space and time derivatives. So this is the prototypical wave equation in vector form, and we have on the left the acceleration term u double prime, so that's a second time derivative, and then here on the right we have 2 types of second spatial derivatives. And when we think about the properties of how we record seismic time series, the time series are typically sampled at high rates and regularly, which means that we can actually calculate this u double prime term relatively accurately by use of just numerical finite differencing. But the seismic spatial data are sampled sparsely and irregularly, which means that trying to calculate these sorts of terms, which we really need to understand the seismic wave field, is actually incredibly challenging. And there's all sorts of cool techniques that you can apply to the seismic wave field. For instance, you can do seismic tomography without actually doing any kind of inverse problem if you can take these sorts of derivatives directly, but it's proven challenging to apply just because calculating these things is difficult. So we need some kind of interpolation effectively to take our point sensors and turn them into a 3D or 4D representation. But how do we do this interpolation in a way that actually works correctly? Because just naive interpolation doesn't work very well, as I'll show you in a bit. And the idea here is to try to do some kind of interpolation that respects wave physics and therefore gives better results. So this is an example from Zhongwen's 2018 compressive sensing paper, where using a particular basis for interpolation allows you to recover complex waveforms. This is a complex waveform that's actually recovered on the right from this very sparsely sampled point wave field. And it's quite challenging for for me to see the wave field propagating across this array. You can sort of see maybe some features, but it's very difficult to really see how you would be able to get this out without very careful design of the inversion method. So in this case, Strongwen used a superposition of plane waves and a compressive sensing method, which is basically trying to select the minimum number of plane wave coefficients required to represent this wave field in order to create this very high quality interpolation on the right. So in my PhD, I've taken the idea from this paper and tried to expand it to work on real data and also DAS data. So the outline of the wave field algorithm that we have developed is essentially 3 steps. The first is probably the step of any kind of data processing algorithm, which is where a data quality control. So you remove any stations that have bad phases, poor ground coupling, numerical error, something like that. But the more interesting step to these two, so you first transform these time domain signals into the wavelet domain using some kind of wavelet transform, like the discrete wavelet transform. And the reason why you do that is this interesting observation that seismic signals are strongly non-stationary. So you have in this spectral time frequency plot here, you have period of the seismic signal here and time across here. And you can see that in any constant period slice or in any constant time slice, the power of this signal is not constant. So time frequency representation allows us to break down this time signal into an individual pixel here and weight it effectively independently of all the other combinations of time and frequency in order to get the best possible representation of the data. And then so this is in the time domain, and then in the spatial domain, we then apply compressive sensing. So as here, using the curvelet basis. So the curvelets are a particular type of mathematical function that are used to sparsely represent propagating wave fields. They were developed in the early 2000s specifically for these sorts of problems by applied mathematicians. And they allow you to basically represent each of these wavelet coefficients in an optimal way in space in order to interpolate the wave field. And then to create a wave field at any particular point in our domain, now that we've assimilated our observed data, we basically just go back up this chain and we can project then to a 3D data cube essentially of what the wave field is doing, which is then very easy to differentiate as opposed to hard to differentiate. This is a very non-technical discussion of how this particular algorithm works. If you're interested in the details, Strongwen and I recently had a paper in GJI for this on non-DAS applications. So I would recommend checking that out if you're interested in this technique. So for an example of this for point seismometers, we'll look at the Ridgecrest magnitude 7.1 earthquake recorded on the Southern California seismic network. And it's interesting because it has a relatively complicated wave field with high curvature in this domain and scattering. These are HNZ strong ground motion sensors filtered at a relatively long period. And you can see this plot with the wave field 100 seconds after the origin time recorded on the array. And if we just do linear interpolation, say, we can see that the straightforward map of the velocity kind of looks okay, but when we take the derivative, and this is obviously important for things like DAS, because DAS actually relies on the derivatives of our observations because it's measuring strain. You can see here that the Laplacian is really bad. This is non-physical. And so we haven't actually recorded the wave field accurately enough to be able to use it for things. Likewise, something like curvature minimizing spline might be slightly more advanced, but it still doesn't perform well with the Laplacian. But using this compressive sensing algorithm, we can actually get a physically reasonable Laplacian. So we're actually trying to capture, we're actually capturing much more of the true motions of the wave field down to the spatial derivatives using this methodology than using more naive approaches. So what can we do with this in terms of DAS and nodes? So the concepts are to start with the wave field as the fundamental object of interest rather than individual channels. We can optimize the wave field to fit nodes by themselves, DAS by itself, or together simultaneously using compressive sensing. We have ways to optimize the geometry of the deployment to promote compressive sensing solutions. And what I'm really going to talk about for the rest of the talk today is basically using nodes by themselves to create wave field volumes that have accurate derivatives to then evaluate DAS channels. So as I said before, I'm going to use the Brady Nevada Porotomo experiment. So thanks so much to the Porotomo team, because they did an amazing job providing this fantastic data set for us all to use, which has a very interesting deployment where we have lots of co-located nodal stations and and DAS in an aerial configuration. So we can actually access all the components of the horizontal wave field and compare them. And what we can do here is use our algorithm to invert the wave field at the nodes, and then project it onto the DAS by basically taking the longitudinal derivative of the wave field in order to get the axial strain. So we can check, basically what we do first is we correct the nodes for their instrument response. We then do the wave field reconstruction algorithm. We checked using cross-validation that actually, if you take some of the nodes out and then put the nodes back in, you can predict that held out data set quite well. So the algorithm is actually reconstructing the wave field as measured on the nodal stations. And then we take the axial strain rate to compare against the DAS, applying all the necessary magic numbers, etc., to get the actual wave, the response. And we can see that it generally matches the phase and amplitude quite well at most of the stations. So some of the great fits.
2 minutes.
Sure. Some of the great fits here, you can see it fits very well at this 2895, but there are also stations here like 1744 where it doesn't fit particularly well. So if you look at the histograms of these sorts of fits, you can see the uncorrected, I'll talk about this in a second, cross correlation fits relatively well. So this is looking at the cross correlation of the predicted and observed DAS waveforms. So it's relatively well fitting, but there's a significant error in terms of the amplitude in some of the stations. And it's interesting to note, if we break this down by whether it's during the P wave or the S wave, sorry, I should point out this is for the 4.3 magnitude Hawthorne, Nevada earthquake. If you break this down for the P or S waves of that earthquake and across periods, we see a relatively consistent pattern of amplitude misfits. So particularly here in the sort of bottom left of the array and the top right of the array, that seems to correspond to the geology actually of the surface as measured during the array deployment. So there's some kind of sense that the ability to predict the amplitude effect is affected by the near surface geology in this particular setting. So this is the sort of thing we can do with this algorithm. There are more things we can do. For instance, we can try to naively correct the amplitude by dividing basically by this map. And of course, this obviously gives us a better amplitude fit, but it can't do anything about the wave field fit. We can also apply a more advanced theory based on two-scale homogenization in order to try to fit both. And that does a good job of correcting the wave field shape. And if people are interested in that, this is still very early work on DAS, but there's more advanced work on this for rotation measurements in Singh et al. 2019. And this is basically Jan Capdeville's work in general. So there's a review paper by him in 2020 that people should look at. Just very quickly, we can also use optimal design techniques in order to choose nodal locations given DAS, but I think I've run out of time, so I recommend people read the upcoming paper in this, which will explain how to do this more thoroughly, or ask me after this talk if they're interested in how we can do optimal design in order to pick individual point nodal locations given a particular DAS geometry. But that is also something that you can do in the compressive sensing framework, and that's interesting in terms of being able to design arrays around dark fiber. So key takeaways of this, essentially a new algorithm for assimilating DAS and nodes into a uniform data product. Using wave field techniques, we can investigate the DAS response for relatively complex cable geometries. So basically we can do this for the whole array simultaneously without relying on stations having a particularly favorable geometry relative to the DAS cable, which is what previous techniques have relied on. And there's a possibility of optimizing node placement to best combine with a given DAS deployment. So thank you.
Thank you very much, Jack, and for that particular hour that you're doing it at. It's nice to see how much you're being able to do with the Brady Hot Spring data. We are coming to our break now. If anybody would like to ask a quick question, you could just unmute yourself and go ahead and ask.
I think there's one from Eileen there in the chat too. Eileen, did you want to?
Yeah, I'll just ask it. So do you see any way to kind of extend the theoretical framework you're working with to also incorporate some of the like rotational seismometers or things like that? Is it a good fit for that?
Yeah, definitely. So essentially, the advantage of this is that when you are treating the displacement wave field effectively as the fundamental object of interest, then all these subsidiary things like DAS or rotation are just linear transformations of that via differentiation. And so when you combine them all, I didn't show this in this particular talk, but if you combine all of the things together, it essentially becomes like a giant linear inverse problem. Where you have the different types of data correspond to different forms of the sensing matrix, essentially, because they have different ways of sensing the wave field. But you can definitely combine them all into a single problem, and therefore invert all of them together to get at the displacement wave field. So rotation data, you just take the the curl of the wave field rather than the divergence, I guess. So yeah.
Okay.
Cool.
Let me turn the mic over to Casey, who will tell us about the logistics of our break.
Sure. Well, thanks again to all the speakers everywhere, but particularly for Jack. That's so amazing that you gave a live presentation at that hour. And so I know if you don't want to stick around much longer, I'm sure you got to get to bed. But participants, please do ask questions in the chat on the event page, or direct those to Jack either via email or through the Pathable platform. So thank you again to all the speakers in this first session. I'll go ahead and get a slide up here for our break, but we are on break until 12:30 Eastern. So at the half hour, we will get started and try to keep to better time on this next section. So we'll be back and listen to some great lightning talks, and then go out into discussion breakout sessions with those. So thanks again. I think your applause was muted there, Eileen.
Just visual applause.
Yeah, visual.
Same here. Great job.
And if anyone has any questions, I'll be here happy to answer them.
Casey, sorry, I couldn't get the background up for the Sage Gauge. I tried a few times on Zoom and I couldn't change my background, but I'm sure with enough time I will do it.
Maybe there's some limitations on the university side. I know some of the more fun aspects of Zoom, like filters and stuff, are probably disabled.
No, this is my own Zoom.
Oh, it's your own? Oh.
Yeah, no, I should be able to do anything I want with it, but I can't find at least following the instructions, I can't find where to change the background.
Yeah,
anyway.
It should be in like preferences and then virtual background, I think. And then there's a little plus sign button, and then you can add a different file.
Well, mine was telling me to go into the portrait part, but I will work on it offline. Okay. Yeah, good. What time I'm sorry, I wasn't paying attention. What time?
12:30. Can you see the slide? Is it up?
I can. Oh yeah. There is a black box.
Oops.
In front of it. Yeah.
Sorry.
Okay. Yeah. Good. Okay. Thanks, Casey. You're doing a great job.
Thanks.
So just to be sure, you are going to run the video from your end?
Yes, and I'll go ahead and hide. Let me just see if this works, because you can probably see. Okay, hide loading meeting controls. Are there still boxes?
There are two boxes, one on the top right and then one in the left center.
See, and now I'm like, I don't know how to find my Zoom controls. Well, we're on break, so I'm just going to go ahead and try to. I'm sure everyone has seen the slide. Okay, wait. So X. Okay.
I'm trying to present the couple of slides that I prepared, and then I let you share the screen. If that is okay with you. If not, I can try to do it myself. But I'm concerned that I couldn't figure it out how to open.
Yeah, no, it's no problem. Happy to do that. So I guess if I close out all of these, and so now, is that totally clear of boxes?
There's just one. Oh, now they're gone.
Yes. Now it's perfect.
Okay. Yeah, it always just makes me nervous not having my Zoom controls, but I think yeah, so I can get it back just fine. Okay, so I'll do that when it's the video and make sure that, yeah, just since I won't be able to see the chat during this, I'll try to log in on my other Zoom for this meeting, just so that I can actually see the chat while I'm sharing too. But if anything goes wrong, you'll have to speak up because I won't be able to see the chat during the video playing.
Thank you.
Makes sense? And Ariel, yes, I can broadcast that video. I will go ahead and download it now.
Cool. Just note it's like only 9 minutes, so we should probably come back from that break a little later.
Okay.
Like maybe, yeah.
I always feel like a little extra time is is no problem. We can have some dead air, I think. I always just get worried about just so we can have plenty of time for questions and stuff. So I know I don't want to get off. It'll be AGU rules, right? Like where we don't start early, but we'll
Yeah, I mean, he's not going to be there to answer questions. That's the thing. I mean, because he's sending a video because it's like 3 in there.
True. Yeah. Mm-hmm.
That's why I was thinking. I mean, Eileen and I were thinking to kind of push it forward.
I guess.
Okay. Yeah.
Yeah, we could come back like 5 minutes late and then that would work. Okay.
Mm-hmm. Yeah, sure.
Cool. Right, I'm going to make a cup of coffee.
Okay.
I've just updated the slides with the agenda for that break to start or to come back from that break 5 minutes later. And that way I can just screen share during the break. And yeah.
Okay, sounds good. Let me see if I can log in. All right, I think I saw Scott there. So is it okay if I test the audio really quick? Audio and video.
I'm here too if you need my help.
Oh, okay, great. Sorry. Yes, I'll just go ahead and play.
Hello everyone, my name is Julius Grimm. I'm a master's student at ETH Zurich. Today I'll be talking about cryoseismic event analysis on distributed strain recordings. This work was done in collaboration with my thesis supervisors.
Okay, I could hear him.
Sounds good.
Okay. I think I just have to be a little faster at hiding the screen controls. Should have given myself more time at the beginning, but
Okay.
all right. Right? Yeah.
Now.
Okay. So thank you very much. My name is Dante Frata. I'm with the University of Wisconsin-Madison. And we have prepared a set of 7 lightning talks. They are from diverse group of individuals from organizations at universities all around the world. We are going to start with Julius Green from ETH Zurich, and he's going to be talking about some work that they have been doing evaluating cryoseismic events using DAS. William Wilcock of University of Washington will be talking about a community test that's going to be done using offshore fiber optics and inviting you to participate. Boone Hewley, Australian National University, will be talking about direct modeling from the Canberra deployment that we have been working the last few years. Yarin Abukrat of Tel Aviv University will be talking about using high density arrays, DAS, for monitoring shallow velocity analysis. And he's going to be showing some work of trying to detect using a combination of horizontal and vertical DAS array, locate clandestine tunnels. And Andres Chavarria of OptaSense will be presenting some work that they have been doing within his organization on microseismic and strain DAS measurements to evaluate fracture geometry. Hart DeWitt, Colorado School of Mines, will be working on some of the work they've been doing monitoring tailings and using seismic interferometry from DAS data. And finally, Oleg Balishin of CERCEL will be presenting work they have done using distributed acoustic sensing and railway traffic to be able to do geophysical monitoring. After the presentation, the video is going to be about 24 minutes long. Each presentation will be between 3 and 3.5 minutes. And after the presentation, we are going to open the floor for any questions that you may have from the authors. And then we are going to break up in breakout rooms, and you will have an opportunity to select the rooms that you are going to have. Before we start, I would like to point out that the third presentation by Von Hewley, the volume level in the recording is quite lower. There is nothing wrong with your computer. I will ask you to increase the volume in your computer to be able to hear that. Besides that, we are ready. So Casey, I'm gonna stop sharing my screen and it's all yours.
Hello, everyone. My name is Julius Grimm. I'm a master's student at ETH Zurich. Today, I'll be talking about cryoseismic event analysis on distributed strain recordings. This work was done in collaboration with my thesis supervisors, Patrick Peitz from ETH and Eileen Martin from Virginia Tech. The data was acquired on the Rhone Glacier, of which you can see an aerial photo on the left. And ETH researchers in summer 2020 deployed a 9-kilometer long fiber optic cable, which is plotted on the right, and it goes from the acclimatization zone down to the ablation zone. The DAS system acquired data continuously for 1 month with 4-meter channel spacing and 1000 Hertz sampling frequency. In total, this amassed around 18 terabytes of data, so really some sort of automatic processing is required. A quick note on cryoseismology. So glaciers are very dynamic systems, and various glacier processes emit seismic energy. So for example, surface crevices where cracks appear on the surface, or when the glacier is sliding, you get basal ice quakes with stick-slip motion. Here's an overview of the workflow we were following. So after data was collected, it was pre-processed, and features were extracted with array processing techniques. And then the output from this array processing was used as direct input for the clustering analysis. So one of the features we were looking at was apparent velocity. On the left side, you can see an ice quake and a zoom, and there are 2 move-outs belonging to 2 different velocities. And on the right side, you can see a frequency slowness plot here, where you can also see these 2 move-outs clearly separated. But this still is a very high-dimensional picture. What we did then was summing up the energy over certain frequency ranges, for example, from here from 10 to 50 Hertz. And then you get this curve, which shows which velocities contribute how much to that time window. We then did some resampling, so just downsampled the curve and ended up with 20 features showing the velocity content. This was then put into the clustering analysis with hierarchical clustering, and the result is shown on the left for half an hour of data, and we subdivided this data in sub windows with 200 channels and 15-second length. And the output is quite interesting. So all these elongated features, which are colored, correspond to cryoseismic events, and the color gives which cluster they were grouped to. And on the right side, you see representative waveforms for each cluster. So cluster 0 really is just background noise, which is the white here. And then yeah, you get really different types of cryoseismic events, even in the small time window. Thank you for your attention. If you have any questions, I'll be happy to answer them in the breakout room.
This lightning talk is to announce a community DAS experiment that's going to be occurring offshore Central Oregon this fall on the Ocean Observatory's Initiative Regional Cabled Array. There's a lot of interest in offshore fiber sensing in the Pacific Northwest, and I list on this slide some of the potential applications. And I just note the last one, that in the long term, DAS may be an important tool for earthquake and tsunami early warning, both using scientific and commercial cables in the region. There are challenges to doing a DAS experiment in the Pacific Northwest. The first is that there are 2 scientific observatories operated by the Canadians and the US, but neither of these has dark fibers, and the observatories aim to stay operational all the time. And the second problem is that all seismic experiments in US waters need to address security concerns of the US Navy. And for the Canadians, they also have concerns from their Navy too. And that's because seismic observations can potentially record the signatures of submarines. Now, in order to address Navy security concerns, NSF coordinates very closely with a group called the Ocean Observatory System Security Group, and they've developed procedures for seismic experiments, so that the data from autonomous OBS deployments is taken by the Navy and screened within 90 days to remove signals of interest. And for the seismometers and hydrophones that are on the cabled observatories, the Navy has a diversion switch for the high frequency data, and they divert about 20% of that data and then return most of it within about a week. And for DAS, there are no protocols that have yet been developed. Now, the community experiment will utilize a rare shutdown of the ORI cabled array in early November for 4 days. We'll collect DAS data with 3 systems from Aragon, OptaSense, and Silixa, and distributed thermal sensing data with the Silixa system using the 4 fibers that are available in the 2 cables that extend off Pacific City, Oregon. There's going to be extensive on-site security, make sure that no scientists walk off with data, and then the data will be screened. And an important goal of this experiment is to establish procedures so experiments can move forward more smoothly in the future. Now, this is a community experiment, so when the data is screened and released to us in late winter or early spring, it's going to be archived and made available through the OOI data management system, both for downloads of the original data and eventually derived and downsampled products, and also, since we'll be collecting tens of terabytes of data, making copies to disks that people supply. Now, the NSF is funding just the data acquisition, so it's hoped that people will step forward to work on this. And if you're interested, I really encourage you to contact me so that we can coordinate activities. Thank you.
Hi, my name is Vern, a postdoc from the Australian National University. With Brian Kennett, Megan Miller, and Herb McQueen, we present a way to directly model dark strain rate, which is particularly useful for dark fiber arrays that has complex geometry with short stretches of uniform fiber orientation and uncertain ground coupling. We then apply this to a regional event that is recorded by a dark fiber deployment at the Canberra Deep Space Communication Complex. The average strain rate can be obtained by differencing the ground velocity resolved along the cable at the ends of the gauge length. For sources at the near field distances, such as tap tests and local events, there are a few factors that matter. First, the change in the waveform across gauge length can be significant, so the dust does not directly correspond to the ground velocity. Second, for instance, in tap tests, the sources sometimes are not directly on top of the fiber. And lastly, at high frequencies, the perpendicular strain may become significant. So it is important to take into account these factors when we simulate dust. Here we use a numerical integration method in the frequency slowness domain, where we can incorporate stratified layers, different types of sources, gauge length, and the fiber orientation effects. For sources at larger distances, where the change in plane wave is less than the gauge length, the strain rate is the acceleration modulated by slowness along the fiber. So only the fiber orientation dominates. And those can be modeled using the response of a spectrum of plane waves. Here we present a preliminary result of modeling dust signal of a regional event 150 kilometers away. The significant low frequency noise at the site and also the weak event magnitude forces us to use only the higher frequency, which is inherently harder to model. For example, we can see that in order to fully model the scattering and the coda, we need a more complicated regional velocity model. And the poorly constrained Fokker mechanism can affect the P and S wave radiation pattern. However, we can see that the directivity is modeled in the synthetics, where the P and S waves have different directivity effects. We also want to point out that certain parameters in collecting the dust data matters and needs to be considered. So one is to account for the channel averaging, which is a functionality in IDAS to increase wave field coherency. Another thing is that the ground coupling may vary along the fiber, which is an uncertainty, especially coming to using dark fiber, as you can see at the 500 to 700 meter here. Therefore, modeling the waveform can help us to understand where the ground coupling might have changed, and also to account for the gauge length effects where it matters most in modeling near field sources. Thank you.
Hello, everyone. My name is Yarina Bukrat, and I am a PhD candidate at the Department of Geophysics at Tel Aviv University. My research focuses on using dust for near-surface seismic applications. And today, I'm going to show you results from a recent seismic experiment aimed to conduct shallow velocity analysis and use it for imaging a subsurface void. I will start with the acquisition geometry since it's a bit complicated. From the left, there is a side view of the survey layout and a map view from the right. Appears in blue, the DAS array consists of two segments, a surface array and a VSP array. The surface array is deployed horizontally along the x-axis in a surface trench of 1 meter deep. It includes 54 DAS channels separated by 1 meter. The VSP array is deployed inside 4 boreholes that each of them is 45 meters deep, and they are separated by 7 meters from one another. The seismic source was a 5-kilogram hammer striking a metal plate that was activated every 1 meter along the receiver line for a total of 54 shots. The void in gray is elongated in the y-axis through the screen and outside of it. It is in a horizontal distance of 26.5 meters from the beginning of the line and in a depth of 24 meters. In addition, its dimensions are 1 meter wide by 2 meters tall. These are the data from both segments. In the DAS VSP data from the left, the upgoing and downgoing sections of the boreholes are very clear. From the right, these are the first 5 shots recorded by the DAS surface array. Notice that the near offsets are very noisy and suffer from a lack of coherency. It is probably because the shots were very close to the fiber. As a result, I decided not to use them for picking. These are the output velocity models. The VP model from the left was obtained by travel time tomography from both the surface and VSP DAS data. From the right, the VS model was obtained by applying multi-channel analysis of surface waves, the MESW, only on the DAS surface data. This is the void imaging result. It is the result of a 2D S migration on the DAS surface data using the obtained VS model. I chose to present only the S migration results because they are much better than those of the P migration. Most likely, it is because the directional sensitivity of the DAS. Thanks for listening.
Hello, everyone. In this presentation, I will talk very briefly about the development of fractures using fiber optic DAS, microseismic and strain. And I will be using a very exciting data set that uses fibers in horizontal and vertical wells. So this is helping us understand fracture development, not only from a seismic point of view, but also from a strain and deformation point of view. So we're all familiar with microseismic, with seismic data to analyze these types of physical phenomena. In this case, I have, again, 3 fibers. Again, basically, we have a full 3-dimensional borehole network from which we can do our microseismic analysis. So again, I won't get into the details of this. It's traditional earthquake location, earthquake radiation processes. What is exciting is that coupled to these measurements, the DAS sensing is very rich in the low frequency bands. And at those low frequencies is where we're sensing strain responses. So what I'll show in the next slide is basically what happens when we use, in this case, I will focus on only the vertical fiber because this provides very important information about fracture growth. So coupled to that seismic radiation, the fiber again is going to be sensing a strain. So again, in this case, I have my vertical sensing strain, and as these fractures develop, again, they start to grow with respect to time. So here I'm just zooming in a particular stage where essentially I'm tracking the strain with respect to depth and with respect to time. And here what we can see is that we have a distribution of microseismic events overlaying in this specific strain map. And we see that most of those microseismic events are very localized in depth. We see that there's a couple of them that may reach a little bit high, but we can see that beyond that event, the strain keeps growing and growing. So this is exciting because it basically tells us that the fiber is responding to all of the seismic deformation that is undergoing in the subsurface. So from that point of view, basically the fiber is very able to illuminate the full fracture growth beyond the microseismic. The microseismic is actually not as sufficient to characterize the dynamics. And further to that, really the sensitivity, what we find is that the sensitivity in DAS at these very short spatial resolutions really helps us illuminate the development of these fracture networks. So again, this is an exciting technology. Again, this is complementary in the sense that it is allowing us to really understand geomechanical processes. And again, it has applications from conventional reservoirs, induced seismicity, for example, for carbon storage, enhanced geothermal system, the slope instability. So multiple applications from a measurement done with the same unit. Thank you.
Hi, everybody. My name is Charles DeWitt, and I'm a PhD student at Colorado School of Mines. Today, I'm going to be talking about monitoring tailings dams with seismic interferometry using DAS. What are tailings dams? Tailings dams are designed to contain the waste slurry remaining after processing ore from mines. They're some of the largest man-made structures on Earth, even visible from space, but given their piecemeal design, are extremely risky structures. Tailings dams are up to 100 times more likely to fail than conventional water storage dams. And a number of catastrophic tailings dam failures have occurred in recent years, particularly in Brazil, causing loss of life and significant damage to the environment. So mines are trying to do their utmost to prevent any future failures. Some examples: Samarco in Brazil in 2015, nearly 43 million cubic meters of toxic mud was released, and sadly 19 people were killed. Mount Polley in Canada in 2014, Cadia East in Australia in 2018, and most recently Brumadinho in Brazil in 2019. Again, sadly, 270 people were killed following this failure. In many cases, these structures were well instrumented with state-of-the-art geophysical instrumentation, highlighting potential shortcomings of current monitoring techniques. Current monitoring of tailings dams are either based on observations of surface deformation, for example, radar, INSAR, or point measurements, for example, from pore pressure barometers. But it's been shown that by the time changes manifest at surface, for example, it's often too late for any early warning. This has highlighted the urgent need to develop new methods to assess the structurability of tailings dams and prevent any future failures. Over the last decade, the use of seismic interferometry has been widely adopted in crustal seismology to image and monitor the subsurface. The method relies on the reconstruction of the seismic Green's function between multiple sensors, effectively turning one sensor into a virtual active source. This has been shown to be able to measure internal changes in a dam on, for example, a laboratory scale, or detect seepage in a real full-scale tailings dam, for example, from heavy rainfall. It's also been used to image the internal structure of a tailings dam wall. And here, the dense spatial sampling of DAS really enables this with very high spatial resolution. Following our experiment in 2017, we returned to Princes Creek Tailings Dam on the west coast of Tasmania in Australia. We installed 1 kilometer of fiber in a shallow trench and connected a Terra 15 interrogator. We also installed 3 component nodes co-located along the length of the fiber, the red diamonds in this figure. We recorded data for about a month and also carefully surveyed the fiber every few meters, the white dots in this figure. We're currently processing the data from the nodes and the DAS, both measuring time-lapse velocity changes and imaging the dam wall. and comparing the results between the nodes and the DAS. We look forward to sharing these results later this year. Thank you very much.
Dear all, hello, this is Regulation Officer Cell. I'll be presenting the geophysical monitoring of variables with distributed acoustic sensing. I'm presenting company Cell, which has been supplying the seismic industry with different type of equipment, recording and sources since 1956, and working since recently in structural monitoring as well. We address the geophysical problems of variable monitoring for sinkholes, subsidence, and other type of decompaction using the automated sequence of recording the velocities with the noise generated by passage of the trains. This is how the system works. It automatically generates the images as the train passes by. We can do the two types of acquisition. One is with nodal systems using the nodes for the audit, and something that can be cable system for monitoring. Their end image is a processed results where we have a complete map of subsurface under the railways to identify the changes in the structure. And we can also deliver this kind of solutions on the web interface where you can see it on a 4D basis at your convenience. We also looked at the longer monitoring at the longer stretches, and this is where distributed acoustic sensing came in. So we can supply different type of solution there, and distributed sensing was definitely to be tried. We tested one of the projects where we compared different type of cables, straight and helically wound, and also we compared directly the distributed sensing with discrete sensors from Cell. So the results are quite encouraging. We looked at different type of interrogators with different physics of the measurements, and the results also a little bit different. We managed to get from the processing the results that are very similar. This is an example of two interrogators in straight fiber. And we also looked at the helically wound cables supplied by Cell, and we could see that actually, yes, helically wound cables can provide a much better picture because it eliminates the problem of the directional sensitivity. So the results maybe not as good as electronic sensors, but with the helically wound cables, getting very encouraging results. If we compare the pictures, the MSW pictures of the discrete sensors on the left and two interrogators on the right, you can see that the resolution and the quality of the image may not be as good as electronic sensors, but it definitely allows to have a much better long coverage along the railways. If we come at very quick conclusions for this lightning talk, is that the answer is yes. The distributed acoustic sensing can be used for geophysical monitoring of railways, but there are certain limitations. Sensitivity is being one, direction sensitivity is another one. The interrogators on the market currently are getting very close to each other in terms of performances, but still the right choice of parameters is very critical of getting in the right data. Signal to noise ratio stays still very critical, especially at the very small gauge lengths, which is required for the higher resolution projects. You need a high sensitivity fibers and high sensitivity cables that to get a better results, and definitely helically wound cables was a lot of help for the geophysical applications. There is a lot of work happening right now, both in commercial projects right now and Rail Lab, that we'd be happy to share it with you or the further talk. So if you want to contact us. And the last one, probably the question can be asked as well, is distributed acoustic sensing versus the discrete sensors. What is best? There is no right answer. I mean, there are different applications. On some of the applications, the discrete sensors will do the better job. Distributed acoustic sensor definitely has advantages at the longer terms and longer stretches, but sometimes you will need to combine it. Thank you very much for your attention. Bye-bye.
So thank you very much. That concludes all the lighting presentations. Let me start my video. So I would like to open the floor for just some few questions for any of the authors on the lighting presentations, and then we are going to have breakout groups. So we are going to ask each of you to assign yourself to different groups to have a more discussion. But at the meantime, if anybody has any questions before we send you to different breakout groups. I do have a question if nobody else does have one. I have a question for Yarim, but I don't think Yarim is here. So maybe Ariel, maybe you can give us an answer for that.
Yeah, I can try.
Okay. So a couple of questions related to what is the wavelength that you are using for this? What was the main wavelength of your signals? Because that will be related to what you are going to see on the anomaly on the side.
Yeah, so generally speaking, the problem is that we're working in pretty small experiments, but the subsurface is very attenuative. So that means that high frequencies die off quickly. So we usually can see, let's say in surface to borehole, we can probably see 70, 80 hertz. That gives us a wavelength of maybe 4 or 5 meters on the shear waves. And when you're doing diffraction, I mean, you can probably assume that the void acts as a diffractor. And in that case, then you can probably see something that's reasonably the right size. But it is indeed a very big problem.
Yeah, so it is a challenging problem. You know, like you put a high density of sensors and actually very, very close to the anomaly. So that is why you can see it. But you know, if you don't know what the anomaly is, it's quite challenging to find.
Yeah, absolutely. We find that, I mean, yeah, more than a few tens of meters away from the anomaly, it becomes basically impossible to see. Absolutely, yeah.
So, any other question for?
There's a question in the chat by Noah Fardhall. I don't know if you want to ask that, Noah, if you want to unmute.
Hi. Yeah, I just wanted to know if it is possible, it will ever be possible to use the marine cables for earthquake early warning, because we cannot really wait for the Navy to scan the data first, to screen the data first. So I wonder if there's a workaround for that. Thank you.
And the answer is yes. The earthquake early warning really just requires derived parameters. Basically, that there's been a big increase in amplitude. And so that data can be obtained on the secure side and passed instantaneously to an earthquake early warning center. And the Canadians are already doing that with conventional seismometers and accelerometers with offshore data. So I don't think that's a problem.
Thank you very much.
So I do have a question for Hard DeWitt. Hard, if you're there.
Yep.
So are you using body waves, or you are also using surface waves to do the imaging of these levees?
Mostly surface waves. So yeah, mostly surface waves. So the imaging work follows sort of a similar workflow to sort of ambient noise surface wave tomography.
Do you also combine with the distributed temperature sensing?
No, this was just strain measurements or strain rate measurements.
Thank you. So, question from
actually, could I ask a question to anyone in the audience? It's more of a practical question, and it relates to hardware. Generally, we're dealing with large data sets. People are talking about terabytes, and are practitioners mainly using spinners to access their data, or are they turning to SSDs and faster storage tools like M2 slots to access and process their data really quickly? So I'm interested in kind of hardware users or practitioners are using to kind of store their data and access it, process it.
I'll say that for some upcoming experiments in Alaska, we're using SSDs.
I can comment, Andres Chavalia from OptaSense. From the interrogator side, certainly SSDs provide superior performance, But on the larger, the issue is cost. Once you start accumulating terabytes and terabytes of this, it will become expensive. So we still, I'd say for most large commercial applications, we're still running commercial spinning drives, but SSDs are significantly faster. And I can say that I use, in general, the faster data rates when we write them. They like SSDs better, but you do have the issue of the cost.
Great, thanks.
Any other type of comments or questions before we move on to the breakout groups? Okay, so with the, let me share my screen. Oh, thank you. So we divided this in three different breakout groups. They are assigned to different papers here, and so we try to assign a group of interest, and I apologize if you don't feel that they're well represented, but we have, for the first group, we have three papers: the cryogenic event analysis on distributed stream recording by Julius Green. The second paper is the community DAS test on the Ocean Observatory Initiative Regional Cable Array by William Wilcock. And finally, direct modeling of DAS from the Canberra deployment by Boon Hu Lei. And this breakout group will be led by Richard Hatch and Casey Otherhall. The second group, the second breakout group is the papers by DAS for shallow velocity analysis, Yarim Abukrat, and the paper by Andres Chavarria, Understanding Fractal Geometry from Dash Microseismic and Strain, and that will be led by Ariel Lelouch. And finally, the group that I will be leading will be monitoring tailings dams with seismic interferometers using DAS, and geophysical monitoring of railways with distributed acoustic sensing by Oleg Balishin. So I will open the breakout groups, and you can self-select in which group you would like to go, and you will have time, about half an hour to have discussion, and probably after we finish with that, we are going to have a few minutes to be able to have a little bit of discussion for the whole group about comments. So let me open the breakout groups. The breakout groups are open right now, and please select yourself and unmute yourself and open the camera so we can have a good discussion about the different groups. Thank you.
Thanks, Dante. And I can go ahead and share the breakout thing just to have that up so you can join your room.
And if anyone is having trouble joining a room, if you put into the chat which room you want to join, I think we're able to assign you.
By some miracle, I think it's actually working. But if anyone's having issues, let me know.
No requests yet.
There's one here from Tom.
Oh, okay. Is
Tom
it in the Zoom chat?
It's in the Zoom chat, yes.
All right, I think I just assigned Tom.
William Wilcock wants to be in group 1.
Eileen, can you put me, Herb, into one?
Sure thing. All right, I see Daniel Wells requesting room 2, so I'll do that. All right, I see Ariel's request for room 2. And Rob Mellors.
Into two.
So Will, it looks like you've been invited to room 1. And I think there should be a pop-up that you might have
Yeah,
to.
I saw that for about a second and it disappeared, and I
Oh,
don't seem to
no.
have the pop-up anymore. So
Okay, let me try moving you and then moving you back.
We got Chad's request, I think.
Did that work, Will? Yep, okay, he's gone.
Oh, and I see Ishmael's request on 1.
Okay. Do you see, let's see, 9 people unassigned, or how many, 8 people unassigned?
Yes, 8.
Yes.
I know one of these is Herb's other computer, one of them's me. Possibly 2. Okay.
All right, is it okay if I go ahead and join room number 3? So I'll just move over there.
Okay.
All right, thanks. Oh, and I guess I'll come back to this room a few minutes early. So I'm gonna come back at like 1:40, and then we'll bring everybody back in at a little before 1:45 before our break.
Okay. If you want, you can just give me the word to close all rooms and it'll just bring everybody back.
Oh, great.
I can
Okay.
even send a message saying I'm going to close all rooms in like 2 minutes, like give them a 2-minute
Oh,
warning.
that would be wonderful. Yeah.
Okay, so just let me know when to send the 2-minute warning.
Sounds good. Thank you.
Okay, you're welcome.
All right, and I will probably join a room momentarily here. Surprised
Yeah.
that more people didn't want to go to 3. I'm supposed to
and-
be moderating 1, but
Well, what about the people that aren't going into a room?
so I'm assuming they probably stepped away and they might ask to be placed in a room later.
I think it's
Hi.
Hi. Yep.
Hi, I'm E. May I ask to go to William's room?
Sure. So 1.
William Willock.
Oh wait. Yeah. Yep. Okay.
Okay,
Got
thanks.
it. Mhm.
And Casey, this is Scott. I'm not able to assign myself.
Okay, where would you like to go?
It sounds like 3 need some people, so you can send me there.
Okay.
Sure.
Done.
There we go. Thank you.
Thanks, Scott. Okay, so I think we're just down to 1, and if they come back, then
Alrighty, I'll send them off.
okay. Thanks so much. I'll just leave this slide up though, and I'm going to use my other account to go to room 1.
Okay.
All right. Bye.
Bye.
Okay, well, actually, I can't seem to find it on this one.
Do you want me to send you?
Yeah, could you send my the one that says second?
Okay, and you want to go to which room?
The first one, please.
Okay.
Thank you.
thank you. I don't know if we are waiting for other people still in the room or everybody.
I think people are starting to come back in. I've got a slide to share during this break. So let me put that up. There we go.
So we have like a couple of more minutes before the break. So I wonder if, Rachel, do you have anything to report from your group?
Sure. Yeah, we had some good discussions last about different coupling issues that different experiments run into. We also talked a bit about using live fiber instead of dark fiber to try and get around some of the issues of not having enough dark fiber around. So hopefully we can find an expert for the next workshop on how to somehow use live fiber for doing DAS.
Thank you. Ariel?
Yeah, so I would say we heard a lot and talked a lot about the FHDS2 experiment, which is a very cool experiment about fiber in unconventionals. And I just learned that data is going to be made public probably towards the end of the year. So if you're interested in looking at fracture growth and very interesting aseismic deformations, apparently, look up HFTS2. And also on the on the shallow side, it's interesting what happens when you look at I think when you look at DAS data with a gauge length longer than your wavelength and things that start to happen then. So that's like also another more theoretical discussion, but also something that's important to keep in mind if you're interested in very shallow stuff.
So in our group, we were discussing quite a bit about the issue of installing the location of the design of the installation of DAS into tailing mine, and where it's supposed to be located and what type of information you are going to get, but also considering what the owner of the tailing dam may consider to be safe or not. These are structures that they are high risk for the mining, so trying to be able to install, for example, at the top of the mine is something that people are not particularly interested. So we talked quite a bit also about what type of observations we want to do and what type of monitoring. And typically it appears that the best way to use DAS data is to be able to monitor the change in stiffness and the change produced by the localization of seepage and the reduction of effective stress at different points that will be related to changing shear wave velocity in particularly, because P wave velocity will be pretty constant under saturated conditions. So we'll be talking about that. It was quite interesting. Hart has shown his work on tailing dams in Australia, but also we have Suzanne from Calgary, Canada, that they are also monitoring another tailing dam there, and we're expecting to see cool results. And that as part of the research coordination network, I try to invite them to participate on the engineering working group. We need more people in that area where we don't have, so it's going to be interesting. So I would like to open the floor for any other lasting comments before we go to a break. Any other suggestions, comments? If not, Eileen, you want to take over and decide what we're going to do next?
Yeah. So we're going to go on a little break until 2:10, and then we've got 3 really exciting talks after that. We're going to have one on how small can you detect with DAS, case study in the Boso Peninsula, so especially looking at sort of how sensitive DAS is to earthquakes. That's by Johannes Nuara. Then we'll have a talk by Veronica Rodriguez-Tribaldos on aquifer monitoring using ambient noise recorded on DAS that's in a dark fiber array. And then we'll have a talk by Thomas Hudson about DAS in Antarctica doing icequake full waveform source mechanism inversions. And so I know there were some questions in the chat earlier about ways to do source mechanism inversion. And so hopefully that's going to be of interest to some of you all. And then we'll have some overview of sort of the DAS RCN, what's going on in the community, how you can get involved. And so yeah, we'll see you all back here at 2:10. if you're one of the speakers and you want to do any kind of screen sharing or sound check, feel free to stick around. I'll stay on for this break. So see you all soon.
Before we move on, I would like to thank everybody who participated on the lightning sessions and all of you to participate on the breaking group. Thank you so much.
Thanks, everyone. See you in a bit. And then
recording.
Casey, you can go ahead and share screen. Thanks everybody for coming back. We've got 3 exciting talks for you all on different applications of DAS, and also a talk on how you can get involved in the DAS Research Coordination Network and other events going on.
Eileen, did you want to introduce this one? And I can then hit play.
Yeah, so
No, I can do it.
Or whoever was going to. Sorry, I'm ready.
Yeah, never mind.
Play when
Let's stick to the plan. Yeah, so the next talk is going to be from Johannes Nuwara from the Wright Corporation. He sent a video because it's 3 a.m. I think in Indonesia, where he's from, and he's going to talk about detecting DAS over vertical boreholes, a case study from the Boso Peninsula, focusing on the detection capabilities.
Hi, everyone. I'm so glad to meet you all here in the SAGE workshop for DAS. My name is Johannes Nora. Today, I'm going to present our research that we work on, Research Institute of Innovative Technology for the Earth in Kyoto, Japan, entitled How Small Can You Detect with DAS? A case study in the Boso Peninsula. In this presentation, I would like to outline there are 6 key points that we are going to discuss. The first one, I'll begin with the reason why we detect earthquake using DAS. And then I'm going to show the field setting of our instrument that we have in Chiba, in Japan. And then the waveform response of DAS to natural earthquakes and how we detect events, the spectral content, and the detectability dependence on azimuth. So the first question that we might ask is that the reason why we use DAS for studying earthquakes. Earthquake is an important subject that we are using to study the internal structure of the Earth. And the efforts that we have made so far is that almost all parts of the world on the surface has been covered by lots of sensors. But in some places where access is quite impossible to reach, for example, on the ocean, and in some places where we can see here the sensors are not there, it is because the cost of maintenance and the cost of installation is too, well, it's not too affordable. So we need a more affordable solution to cover this part of the world. So we are using DAS. DAS stands for Distributed Acoustic Sensing. It is a fiber optic cable instrument where we don't use discrete geophones or sensors, but we use the whole fiber optic as our sensors. So the benefit is that we will have a denser array of sensors along the fiber cable. Now, here's the field setting of our DAS in Chiba. In general, we have 2 wells. The first well is a 250-meter well, where we install 2 DAS, the straight cable and the helically wound cable. So there are 2 types of cable in this 250-meter well. And then the other well is the 880 meter, where we install another straight cable inside. And you see here, this is the diagram or the schematic of the wells. Here is the result of the waveform response of this tree DAS instrument to natural earthquakes. You see here the difference among these three type of settings. And if you see more clearly, we can see that HVC, or the helically wound cable, provides less noisy data, but weaker amplitude response. And then the straight cables, so both STC and BC, so STC 250 is for the numbers here represent the depth of the well. So the straight cables provide stronger and clearer response. And you can see somewhere over here, this is the tube wave, and then this is the multiple wave, where in the BC, it shows less multiples. Here is the result of the P arrivals for these three settings, and then this is the S arrival for these three DAS instruments. So we are using the STA, LTA method and the STFT, or short time Fourier transform, to detect the event for these three DAS instruments. And then we also made a plot of waterfall plot to see the spectral content in our data. So if you see more clearly here, we can identify some noises. For example, there is an interesting pattern here, the stripe pattern. So it turns out that this stripe pattern is the noise caused by the completion. So because some parts of the well has a poor cement integrity, and the deeper part of the well has a better cement, so it turns out that in the poor quality of the cement, it will appear as this stripe pattern. And then there is a shallow noise here. This is because of the near surface noise. And we can see the four corner frequencies, where here is the background noise and the PS arrival, and the completion noise is the highest noise in this data. And then one of the interesting thing is that here we have three events with magnitude 1.4, 1.3, and 0.8. The interesting thing is that here, if you see the 0.8 earthquake compared to the 1.4 magnitude, the 1.4 magnitude has smaller or weaker amplitude recorded than the smaller magnitude. So the question is why? If we see the figure on the right, you can see the azimuth of each events. So for event 3, this is the azimuth, and for event 6, this is the azimuth. So for this azimuth, it turns out that the amplitude appears weaker than this azimuth. So amplitude depends on azimuth, not only epidistance or depth or magnitude, but it clearly and strongly dependent on the azimuth, because the Earth is very heterogeneous. There is a crustal velocity heterogeneity and attenuation. So we have to focus when we would like to install our DAS to study the earthquake. We have to also study the crustal velocity and the attenuation structure. So what we are getting here, the helically wound cable provides less noisy data but weaker amplitude response. And then the straight cables provide stronger and clearer response. It is significantly affected by cement integrity. So it turns out that the poor completion creates a kind of stripes pattern noise. And then the DAS, we find that the DAS is still able to detect earthquakes down to 0.8. So this is a really interesting finding. It is really able to detect earthquakes down to 0.8. So this is a really, really small earthquake. But we have to also concern that the detectability of DAS depends on azimuth. So not merely based on the epidistance, magnitude, and depth, but it also depends on the azimuth. So that's all for my presentation. Thank you for attending. If you would like to contact or asking about some other details, you can reach me out in email or in LinkedIn. Thank you.
Okay, I think that we will then now move on to our next speaker. Ariel, are you?
No, I'm introducing Veronica.
Sorry, Herb, sorry. I'm gonna mess everyone up.
Veronica is a research scientist at the Lawrence Berkeley National Lab in the Energy Geosciences Division. And she's going to speak to us on aquifer monitoring using ambient seismic noise recorded on dark fiber DAS. Veronica?
Yep, thanks. Can you hear me? Yes.
Yes.
Okay, great. Yeah, so thanks for the introduction, Herb. So hi, everyone. Good morning or afternoon or evening, depending on where you are in the world. So today I will be talking to you about how we can combine ambient seismic noise and DAS deployed on dark fiber to monitor groundwater table elevation changes and in general aquifer dynamics. So let me change here to my laser pointer. Okay, so I think we all know that hydrological basins are actually very complex systems. There are a lot of natural and anthropogenic processes that are interacting with each other over large distances, but also they change at very short wavelengths. And these processes, they are not only changing over space, but they also vary over time. So currently, the most common way of tracking these changes, of monitoring these systems, is basically making direct measurements of groundwater table elevation in wells. So here I have an example of a distribution of wells in the Sacramento Valley, in the Central Valley of California in the US. And we see that it's kind of sparse. And even at locations where we have measurements, like for example, in this well here, we can see that over several years, maybe we just have a couple of measurements every year or so. So this is going we are going to miss some information when we want to look at some of the details of what is going on at shorter distances and then more often in time. So there is definitely a need for developing a tool that can track these changes at high spatial and temporal resolutions if we want to develop effective ways of managing water resources. So recently, geophysical techniques have been used for monitoring changes in groundwater systems. So here, and in particular, geodetic tools have been very common. So here on the left, we have an example from a review by Frappart et al., where we were showing that you can look at changes in observations of gravity from the GRACE mission to track changes in terrestrial water storage, for example. So these are actually, these studies are quite successful, but they have the limitations that they have spatial resolutions limited to tens to hundreds of kilometers, and the temporal resolution is monthly at its best. So in order to overcome these limitations, some groups are using INSAR, where you can detect very small vertical motions that you can then relate to, for example, changes in aquifer volume. So here we're looking at an example from a study by Basco et al., where they use INSAR measurements in combination with measurements of groundwater in wells to invert for changes in the volume of the aquifer. So here the spatial resolution we're talking about is about hundreds of meters, and temporal resolutions in the order of 6 to 12 days. So it's better than the gravity, but still we are looking at kind of regional changes. And finally, seismology has been a geophysical technique that has been recently also used for tracking changes in seismic velocities in the subsurface that then can be related to changes in the dynamics of the aquifer on the elevation of the groundwater table. So here we have an example which is quite well known by Clemens and Denol, where you can see changes in the relative seismic velocities, here labeled as dV over V, that are correlated with changes in the groundwater table, which are in blue, over several years. So we are looking here at seasonal changes and changes in the order of tens of meters. So they did that in the San Gabriel Basin here in Southern California. And what we can see is that in this map area, which is about 30 by 30 kilometers, we have like 7 or 8 seismic stations. So again, we are looking at kind of large scale or regional changes. So if we want to know what's going on, for example, in this area in particular, we would be missing that detail. And this is where we think that DAS can actually come into play because of this large coverage provided by these arrays, but also the high density of measurements that it provides. So here I'm going to show some results from an experiment that we conducted a couple of years ago in the Sacramento Valley in California. We were recording continuously ambient seismic noise data along this dark fiber, which was about 22 kilometers going from the city of West Sacramento to Woodland. And we were recording at a spacing of 2 meters with a gauge length of 10 meters at a frequency of 500 hertz. And we recorded continuously for about 4 to 5 months. So here we are analyzing 3 subsections of the arrays that I'm labeling A, B, and C. And in order to investigate changes in relative seismic velocities underneath these sections, so we are tracking changes not only in time, but also in space in these different regions of the basin. So this is a typical measurement of the ambient seismic noise along this array. So we have time on the y-axis and distance on the x-axis. And these diagonal lines here are actually surface waves mostly that are generated by vehicles that are traveling along roads that are basically parallel to the array or surrounding the array. So this is an area that is very rich in ambient noise that we can then use for further analysis. So these are the 3 sections that we are analyzing. And if we zoom in a little more, we can see again the detail of the seismic noise for the 3 sections, A, B, and C. And here at the bottom, we are looking at the characteristics of their frequency content. So for the 3 sections, although there are some differences, most of the energy is concentrated in this band between about 5 to 20 or 25 hertz, which is the traffic band. So what you would expect. And here on the right, I have included details of aerial photographs that show where the sections of the array are with respect to the Sacramento River, which is here. So this is going to be important for later to interpret our results. So what's important to keep in mind here is that sections A and B are very close to the river, about 100 meters, 150 meters away, but section C is 2.5 kilometers away from the river. And this is going to be important to understand the dynamics of the system and how it related to the seismic velocities. So in order to use this noise to basically look at these changes in seismic velocities, we are going to use ambient seismic noise interferometry, which has been already mentioned before, where we are converting this noise into actual coherent usable energy. So we are taking these 3 sections of 300 meters. We are applying some preprocessing and a bandpass of 4 to 15 hertz. And then I'm doing a cross correlation between the first trace and all of the other traces in this section. So this is giving me a virtual shock gather. And in this case, we are doing that for every 1 minute file that we are recording for these 5 months of recording. So we have here this surface wave that is traveling along the array. Now we do that for all of these 1 minute files. And for each day of recording, we stack all of the 1 minute files to increase the signal to noise ratio to generate these 1 day stacks with a better surface wave signal here. So we are going to end up having 1 daily stack for each of the 5 months of recording. So now we want to compare the arrivals that we pick up in each of these 1 day stacks. So for that, I'm going to select 1 trace at 200 meters away from the virtual source so that we have enough time for the different phases to separate. And I have plotted them here one on top of the other for the entire recording period. So what we can first see is that the arrivals are very coherent and we can see the same arrivals in all of the stacks. And then if we focus, for example, on this time here in early January, we see how these arrivals are actually delayed at this point in time with respect to previous times. And this is very evident in the later arrivals, but not that evident in the earlier arrivals. So we can actually zoom in here a little earlier, a little better, and then we can see how these delays are actually very evident. So the reason why we think that these changes are more evident in the later arrivals is because these arrivals are probably have a high percentage of coda waves, which are scattered waves, which are traveling and sampling the medium many times. So they are able to pick up small velocity changes that you wouldn't be able to pick up with the direct wave. So these are the waves that we are going to use to then take this delay in time and convert it into a change in seismic velocity to quantify those changes. So in order to do that, we are applying the stretching technique, which is very common. And it basically assumes that the trace from today is a stretched version of the trace from yesterday. And the stretching is done according to this equation in which this stretching factor is basically our change in seismic velocity. So we are applying that to every consecutive pair of traces throughout the recording period. And then we are applying a cumulative sum. So we end up having a cumulative dV over V, or change in seismic velocity, throughout the recording period for each of the days. So these are the results for the three sections, sections A, B, and C. And then at the top, I have plotted a record of daily precipitation and daily measurement of the river level of the Sacramento River at these two stations, the precipitation here in blue and the river stage here in orange. So there are a lot of small changes that we are recording that may be to do with the instability of the method, or maybe they are real. But what is really evident are these big changes that are happening here in early January and early March. So if we focus on those, we can see how they actually correlate with big precipitation events and a big increase in the river level in both cases. Now, it's interesting to note that these changes happen in sections A and B, but not in section C. So again, as we remember from the pictures, that section A and B are close to the river and section C is far away from the river. So basically what we think that we are doing here is these seismic velocity changes are reflecting changes in the groundwater table underneath these sections, and that this is somehow related to the river level. And maybe in section C, these changes are not happening, or they are very small and we cannot resolve them. And I forgot to mention that we actually don't have direct measurements of groundwater table for the entire recording period, but the river level can be a very good proxy for groundwater table, in particular in this location. And we have done some study with historical data that actually proves that. So the next step would be to try and understand where these changes are actually occurring in the subsurface. So to do that, we take a one-day stack for section A, and then we calculate the dispersion spectra. And from that, we calculate the one-dimensional shear velocity. And once we have these two pieces of information, we can calculate velocity kernels. So these kernels are basically telling us where in the subsurface we are more sensitive to. So those changes in the seismic velocities we see, where they are occurring. And based on the frequency peaks that we see in the dispersion spectra at 4.5 and 6 hertz, we are plotting the kernels for these two frequencies. And we see that actually these changes seem to be occurring at depths of about 10 to 30 meters or so. And from previous measurements, we know that the water level is it's at the depth of about 4 meters during the time that we are recording. So basically, these changes are happening in relation to changes in the groundwater table, but not at the interface of the groundwater table. So we're trying to explain that by looking at this little cartoon. So when we are actually increasing the river level, there are a couple of things that can happen. So one would be a decrease of the shear wave velocity directly at the interface. And the other effect, which is what we think we're observing here, is that when we are increasing the river level, we are actually increasing the pore pressure. And when you do that, you decrease the effective stress, which decreases your shear wave velocity. And this effect happens at depth, and it decreases as you go deeper, because then your lithostatic stress is basically taking over. So based on the kernels, we know we are somewhere around these depths. So basically what we are seeing are these pore pressure effects. Now, to validate this hypothesis, we conducted a simple rock physics model where we calculated what would be the change in seismic velocity that we would observe if we would only have this pore pressure effect. And we are using this river level as a proxy for the changes in the groundwater table. And the results are shown here. So we have in black the observations from seismology in section A, and in red, in blue, the changes that we estimate with the rocks physics model at the two depths of maximum sensitivity based on our kernels. So we see that we are actually capturing the main changes using this rock physics model, that we are reproducing what we see in the seismology observations, except for this kind of discrepancy here where we are estimating a recovery of the velocities that we don't see in the observations. And we think that this is probably because the rock physics model is kind of simple. We're assuming everything is sand, And we know that we have some clay here, so we would need more details on the lithology of the area to make a perfect model or a more accurate model. But we are basically quite convinced that what we are imaging are these pore pressure changes based on this little test. So this takes me to my conclusions. I think I hope I could show you that DAS in combination with ambient seismic noise can actually be a very powerful tool to track changes in groundwater tables and aquifer dynamics. And this large coverage in combination with the high density sampling is actually, it gives us the opportunity to monitor changes at scales that are relevant for groundwater resource management. And of course, there are still some challenges. So there are uncertainties in the actual links between the velocity variations and the hydrological properties. And of course, I think we've talked about this before, that there are these large data volumes that we need to deal with before we can use this as a real-time tool. And I think I'm going to stop here, and I'll take any questions if you have any. Thank you.
Thank you very much, Veronica. We're open for questions. I think you can just unmute yourself and ask it. Veronica, I believe the correlation with groundwater levels, but when I look at the time series of the river stage and the velocity response, if anything, on that really large increase in river stage, it leads your velocity change. Would you agree? And if so, what might be the explanation?
Let me find that. So you think that so you're saying that the change happens before the change in velocity, or
if anything, yes. If you look at the river stage
right.
at the top, the peak is just somewhat ahead of the minimum in the delta V.
Right. Right. Yeah. Yeah. Well, I think we don't have a lot of the, so unfortunately we don't have a lot of the groundwater level information here. So we need to go with the river, and we go by the hypothesis that we are seeing this connection between the river and the ground surf, the subsurface underneath the array. But probably these things don't happen instantaneously. So there will probably be a delay between, if we're thinking that there is some water connecting to the floodplain, there might be some delay. And that's why we see the velocity is actually changing a little bit later than when we see the river level actually.
So you could actually try to calculate a hydraulic diffusivity for the diffusion of the river water to your
yes,
surface location.
Yeah, I imagine you could, but I think we probably would need a bit more detailed information on the subsurface properties to actually be able to do that. But yeah, I think if you have enough information, I think you could, yeah, definitely you could do that.
Well, I was just thinking 130 meters squared divided by whatever that time difference might be.
Right.
2 days. I mean, it'd be an estimate.
Yeah, 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 you could do that. Yeah, that's true. I haven't done that, but yeah.
Anybody else? Okay. I'll pass the mic on then to Rachel.
Awesome, great talk, Veronica. So our next talk is going to be by Thomas Hudson, who is a postdoctoral researcher in the Department of Earth Sciences at Oxford. And his talk is titled DAS in Antarctica, Icequake Full Waveform Source Mechanism Inversions. So go ahead, Thomas.
Thanks, Rachel. Yeah, I'll just share my screen. Can you see that okay? I'll put it onto presenter mode in a second now.
Yep, you can see that.
Great stuff.
That's good.
Cool, brilliant, thanks. So I'm going to talk to you today about a DAS experiment we did in Antarctica. It was in 2019, 2020. And we've used this data to look at full waveform source inversions, which is going to be most of what I talk about today. I'll talk briefly about what icequakes are for those of you who don't know what they are, although I guess we've seen at least one talk already kind of about icequakes. And I'll talk a bit about the experiment. I'll then move briefly on to talk about just our way of detecting, although I think there were arguably some better talks given earlier on detection, but it's quite a tough problem, and quite an important problem. So I thought I'd just give you a brief overview of that and how we do it. And then I'll move on to the kind of crux of the talk, using DAS for earthquake source inversions. So firstly, icequakes. I'll just get my pointer. What are icequakes? So icequakes are like earthquakes, but they're caused by the deformation or movement of ice over say, well, with ice or bedrock. Here's a glacier, an outlet glacier flowing into the ocean. And you can see icequakes will be generated by these crevassing sources here. They'll be generated by calving events for these big icebergs, but they'll also be generated by ice flowing over the underlying bed via what we call stick-slip motion. And that is what I'm interested in using DAS to try and invert for. And I should say, really, the motivation for all this work is if we can constrain these source mechanisms better, then we can look at how fast this ice can flow into the oceans. But also another motivation for me is the seismological methods, because if we can invert for source mechanisms, then they could be useful for, say, hydraulic fracture, stimulation experiments, and other things. So here's the experiment. We had a configuration of two geometries. We had a kilometer long fiber in a linear arrangement, and most of the data I want to show you today is from that arrangement. But we also had a triangle laid out with sort of 300-meter sides, deployed on a 2 kilometer thick ice stream in Antarctica, the Rutherford ice stream, and we had co-located geophones. We had about 10 co-located geophones. Well, 3 of them were located on the fiber, which were useful for calibration. We used a Silixa IDAS with a gauge length of 10 meters and a sampling rate of 1,000 hertz. And we buried the cable. I know there've been some discussions earlier about coupling. We found burying the cable extremely important. If you didn't bury the cable, you basically got no signal in our location. It was just all wind noise, which if you're interested in wind is great, but we weren't. And the final thing I want to say on this slide is that what's generating the icequakes. This is what I have as a picture in my mind. And if you take a picture through the talk of what's going on at the earthquake source, it is this really. This is a subglacial conduit in Svalbard. Fortunately, it was winter, so there's no water. But you can really nicely see what's probably at the bed of Rutherford. You've probably got ice with some clasts in it being ploughed through a till or scraping against bedrock. And it's this scraping against till or bedrock that's what's generating these icequakes. So yeah, a brief message on detection, I guess. We use an STA LTA algorithm, a bit like the talk by Johannes about half an hour ago. But we do one extra thing, which I think makes our detection method quite useful for DAS. And this method's Quake Migrate. It's an open source piece of software we've released, so feel free to go and use it if you're struggling to detect earthquakes with DAS, or drop me an email if you need help, because it's a bit complicated sometimes to use. But what we do is we calculate an onset function, which is the STA LTA values, but then we migrate them back through space and time and search for a coalescence of this energy over multiple stations. And that search over space and time for coalescence, or a multiple of energy, is really important for this method, because you shouldn't be able to find coherent noise, or at least we hope not. But a genuine earthquake should have coherent signature, which we can detect. So that's how we detect the data, and we treat every channel individually. And there are better ways to do this now, and we've got new algorithms coming out to watch out for maybe, but this is kind of the bog standard one that I've been using. Here are the earthquakes that have been detected. This grey line here is the bed, and you can see the earthquakes are located at the bed. And we're going to use a couple of these earthquakes and try and invert for their source mechanism. And here's the array on the surface. There's the line array. And the ice flow, I should say, is flowing this way. So sort of 158 degrees relative to north. So a little bit about source mechanisms. Apologies if you're a seismologist who looks at source mechanisms all the time, but I thought I'd give you a brief overview for those who aren't familiar with them. We're looking mainly today at double couple source mechanisms. In fact, the inversions I'm going to show you are all DC constrained. That's how we refer to it. And these are basically a block of ice sliding over, well, a block of, you've got two sides of a fault sliding over one another, but remotely to the source they are coupled. Alternatively to this, you could have a single force source. These are model things like landslides, And you can have a full moment tensor, and then these are variations on a full moment tensor, basically. But a full moment tensor would describe things like fracturings, so you might want to invert for a full moment tensor for things like hydrofracture studies where you're opening or closing cracks. But yeah, we're looking at double couple sources. So here's the example icequake that I'm going to really show you and take you through our method and how we invert for the source mechanism of it. This is the main icequake we're going to concentrate on. And it's shown by this yellow star here on the map plot and in the depth plot. So it's at the bed. It's pretty much exactly at the bed. Maybe take my word for that, but we can talk about that afterwards if you want. And we're going to use this linear array, this 1 kilometer array, and we're going to use the geophones separately to try and compare the results. So here is the data along the DAS. So we've got nearly 1,000 meters of data, and on the y-axis is time. And we can see immediately, this is the S wave coming through here. We've got a fast shear wave and a slow shear wave, and this is due to anisotropy, which complicates some things somewhat, but I'll talk about that in a slide or two's time. We don't observe any P waves, and that is because we've really tried to search hard for them, because it'd be great if we had them, but we don't observe them because we have a homogeneous ice layer of about 1,900 meters, and then the top 100 meters of the glacier is actually, or the ice stream, is actually what we call a firn layer with snow that's got a much lower density, sort of 300 kilograms per meter cubed at the top, going down to the ice density of 900 at 100 meters depth. And this causes the rays, the P rays to, well, it causes all the rays to dip vertically upwards, and that ruins the sensitivity of a horizontal array to vertically polarized P waves. So yeah, so we didn't detect any P waves, but we can still do this inversion on S waves. In fact, it's actually very effective. So here's our method. This is the wordy slide, and I've got a picture slide to kind of sum it up if you don't like words. I don't like words. But what we do first is we first downsample the DAS data, and that's because this data is huge, and everyone's talked about the problems of size of DAS data. We downsample it every 10 meters, which represents the gauge length in this data, so it shouldn't have too much impact on our inversion. We then filter the data. We apply a bandpass, FK, and a bandpass filter. Or depending on what the data's looking like. And then we generate synthetic waveforms to compare to the real waveforms. So we've got this observed data, and we need to generate a modeled data to compare to that. We get our model data, and we get it for single moment tensor components individually, and then we can perform an inversion to work out what proportion of each of these is in the inversion, is the best fit for the inversion. And then we apply an anisotropy correction, and that's it's correct for this fast versus slow shear wave issue, which is non-trivial, and that's probably one of the greatest sources of uncertainty in this inversion. We then rotate the synthetic data. Again, this is a theme that's been developing throughout this workshop today. We rotate the synthetic data into the DAS parallel axis, and we convert the synthetic data to strain rate, which is again another thing we've been talking about. You can do that conversion either way. You can convert the model data to strain rate, or you can convert the real data, the DAS data, to velocity. But whichever way you do it, you've got to be consistent, and you've got to make sure you've done that conversion correctly. And then we perform a Bayesian full waveform source inversion. And this is just some pictures to summarize that. And what we do is we basically have this source, it radiates seismic energy. And we compare the real data, which is the black data on here, to the red dashed line. You probably can't see it, sorry, it's a bit small, but that is the model data. And we compare all these waveforms for every DAS channel. This is for a geophone, so it's got 3 components. DAS, we only have 1 component, but we have many, many channels, and we can then perform an inversion using this equation here. We know the Green's functions, and we're inverting for this second order tensor. Before I show you the results, I just thought I'd mention this paper here. It's a great paper that was released in 2019, and this details kind of a theoretical approach to this problem. We've very much taken a data-driven approach, but this paper is well worth reading if you're interested in kind of the theoretical considerations you have to think about with this kind of inversion. So here are the results. These are the results for the DAS data. So here is the observed data. You can notice it's very noisy data. I don't know why our data at Rutford is so noisy. Geophone data for icequakes at Rutford is very clean, but this is very noisy. Here's our model data. And again, the scatter is due to the way I line up with the traces because it's an automatic alignment method. But you can see the difference. There's very little coherent energy. There's a little bit of coherent energy in some of the fast S arrival, But other than that, the difference is pretty incoherent, which means that our model and our data are fitting well. And this is a full Bayesian inversion, so we get out a full probability distribution of the fit between the model and the data. Basically, the thing that I think is pretty amazing about this particular earthquake is that, or icequake, is that this is the slip vector that I've plotted on here. And the ice flow is 158 degrees from north. So this is in very close agreement with the data, with the ice flow direction. And the dashed line shows the uncertainty. So we've got a pretty decent constraint. We've actually very small coverage on the focal sphere. This is far smaller than you would normally hope with a geophone array. So the spatial density of the DAS data is really important for this kind of study. Here's the DAS compared to the geophones. And you can see the geophone, the slip vectors line up for the geophones. We've got I should say that this is maybe a bit of an unfair comparison because our geophone network this year that we did this experiment was not designed for doing source inversions. We could have put out a better geometry, but anyway, nevertheless, the DAS does perform better than the geophones. And you can see the slip vector of the geophones is roughly in agreement with the DAS within uncertainty and roughly in agreement with uncertainty with this 158-degree angle of ice flow, which I would expect theoretically. But you can see that the uncertainty with the geophones is much, much larger, and the DAS is therefore performing considerably better in this source inversion here.
You got about 2 minutes.
Fantastic. I'm just about to wrap up actually, so that's great. Thanks, Rachel. So the final data slide I'll show you is the source inversion results for some other icequakes. I obviously showed you our best result. There are some other results which aren't so great. And this comes down to another point that I think Eileen was talking about in her talk earlier, the sensitivity of the DAS. So sorry, this is a very small plot, but there's a linear kilometer array here, which is what we're using for some of the inversions. And we also use the triangle for the right-hand too. But this linear array is very sensitive. I think the sensitivity lobes are kind of sort of at the ends of the DAS array, if I remember rightly from Eileen's plot. And so these events away from that sensitivity kernel, as it were, don't invert well with the data at all. And we get slip vectors that are all over the place. They generally agree within the uncertainty, but look, the uncertainties are huge. So I'd say there's still a way to go with this method. And it's a pretty challenging thing to do with DAS. So yeah, so thank you for listening. To conclude, we performed a complete full waveform earthquake source inversion using DAS. DAS outperforms geophones in this case, although I've caveated that a bit, but it confirms the value of dense DAS sampling. And inversion is a complex process, especially if we have to account for things like anisotropy. And I guess when you're thinking about, say, hydraulic fracturing in shales, this is going to become very important. And it might become prohibitively difficult to do this, but we haven't used a data set to do that yet. So yeah, thank you for listening. Please feel free to email me if you want to try out any of these methods. The methods are available on GitHub, both the detection and the source inversion code, although they could be more accessible maybe. And these are the relevant papers if you wanted to read more about this study. Thank you for listening.
All right, thanks, Thomas. That was great. Any questions? You guys can unmute.
I have a question. This is Ettore. For your modeling of the green functions, did you use just elastic isotropic medium, or you had to take into account more complicated physics?
Yeah, I used that's a great question. I used an isotropic medium, and then I performed the anisotropy correction by measuring the shear wave splitting on a geophone, and then correcting for the delay time and the rotation angle. So
okay.
That's something we can do with ice because we kind of understand quite well what the anisotropy does in a well, we don't necessarily, but we understand at least what the effect of it is. We use a synthetic waveform code called FK. You can use whatever code you want. If you could invert for anisotropy, if you could get a code that dealt with anisotropy well, a full waveform code, then you could use that instead, and then you wouldn't have to do that step. Yeah, but great question.
Yeah, interesting. Thank you.
All right, any other questions? You might have answered this, Tom, but did you need a specific array geometry in order to collect the source mechanisms? Did I miss that, or can you elaborate on that?
Yeah, sorry, no, I showed you mainly one geometry. It's a great question again. I showed you a linear geometry. Ideally, for a source mechanism, you probably want like a cross geometry with, and then you cover both nodal planes well on a DC inversion, and it will still give you a good result for anything really, for any source inversion. But yeah, we tried with the triangle as well. The problem is the triangle has some really large sensitivity, kind of lacks of sensitivity in different orientations. So the triangle results weren't very good. We did try them on that last slide of data. The two right-hand side inversions were with a triangle, but the linear array performed better. I think just because it's got more spatial coverage of the just in the direction that we need it to be in for the source mechanism. Basically, we got lucky.
Thank you. Any other?
I actually have a quick question. You made a comparison between the geophones and DAS for the inversion. I was wondering if you had any sort of estimate off the top of your head of cost comparison, like if you're designing both of these for moment tensor inversion, how do the costs compare, including say like difficulty and time it takes to install the instruments?
I don't know if you're referring to economic. It's a good question. I don't know if you're referring to economic or computational cost. I guess computational cost DAS far outweighs it. Economically, in terms of instrument costs, yeah, I mean, I would, I'd rather have 100. Well, I don't know. So let's say the interrogator costs, I don't know, $200,000, or to rent maybe, I don't know, $50,000. Those are not numbers that Silixa. I don't know how much it costs exactly, but that's the rough ballpark, right? For that, you can get a lot of nodes, or a good number of geophones. I think I'd always try and use the nodes.
Sorry to interrupt you guys, Tom. We're going to have to move on.
Of course, yeah. Sorry. Yeah, thank you.
Casey and her wrapping it up, talking about the RCN. But yeah, if there's any more questions, hopefully they leave a little bit of leeway time. We can answer those. So go ahead, please.
All right, thank you, Tom.
Okay, can you see my screen?
Yep.
Well, this is the acknowledgement portion of the workshop. So what I'd like to do is describe to you a little bit about the DAS RCN. First of all, it's sponsored by the National Science Foundation, and we certainly like to acknowledge their support. We have a couple of investigators that are leading the effort, myself, Bob Woodward from IRIS, and Scott Tyler from CTEMS. And the person who holds it all together is Casey Adderhold from IRIS. The way we operate is that we have a steering committee of a little over a dozen people that span a wide range of DAS knowledge and application. The goals of the RCN are what we hope happen today, which is to bring together an international, and I know we satisfy that part of their expectation, DAS community of research organizations, industry, technology companies, and government agencies. And through these events, hope to advance the applications of DAS. We have a website. You can find it very quickly, and I'm sure Casey will put it into the chat just by Googling DAS, RCN, and IRIS. And we have a mailing list, which I hope you'd be interested in subscribing to stay abreast of our events. See, my slides are not changing. Why is that?
Sorry, Herb, that's me. I accidentally started sharing and I didn't realize you had narration on these slides. So I just had updated the mailing list, but it should be there now.
I happened to discover that and I managed to turn it off. What I really encourage the participants in this workshop to consider is participating in one of our dozen or so working groups. These got established more or less organically, and I just arbitrarily put them into three categories, examining DAS technology, and one of the really interesting ones that anybody who's going to do a DAS experiment encounters is data management. The instrumentation itself is rapidly evolving and the number of vendors keeps increasing. Machine learning, given the large amounts of DAS data, has a lot of interest. And as different DAS test sites are being developed for research and development purposes, there is a working group that shares the activities at these different test sites. Under geophysical applications, we have a working group on energy technologies, marine geophysics, volcanic and seismic hazard monitoring, earthquake and array seismology, and urban seismology. And then in the non-geophysical, but earth science or engineering areas are hydrology, such as we just heard from Veronica, engineering infrastructure, geomorphology, we just heard Tom Hudson on cryosphere, and geomechanics. So the expectations of each working group are to sponsor a monthly webinar, which I'll describe shortly. They will meet at least twice a year, and we hope they'll prepare different kinds of white papers on their current activities, maybe even put them into their disciplinary newsletters. So under the activities that have occurred in the past are some virtual workshops. There was a workshop at the Sage Gauge workshop last August, and there are some detailed tutorials as that event took place over 3 half days. And then we had a workshop at AGU virtually. These are all recorded, and if you go to that DAS IRIS website, you will find the links to them. We have 2 workshops in planning. There is the Fall AGU workshop coming up in New Orleans. If you have any suggestions for it, please contact us. And one of the workshops that has been delayed as a result of the pandemic is a field course that we are hoping to hold in about a year. Among the webinars that different working groups have organized, there was a data management webinar that occurred a couple of weeks ago, and you can see the other working groups. About once a month, we have one of these webinars that are both on the events page of the DAS IRIS webpage, as well as if you sign up, you'll get reminded of the events as well as the Zoom links. So please do consider at least visiting the website or signing up for the mailing list. And so thank you to Eileen for leading the planning of this short course event. Casey, for your tirelessly managing the logistics for all of our RCN activities, and the planning group, Dante, Ariel, Scott, Bob Woodward, and Rachel for your work on this particular event. And to the speakers, you gave us your latest exciting DAS insights and results, and I'm sure they'll continue to generate some discussion into the future. And for the participants, thank you for giving us your time, energy, enthusiasm, and discussion, and we hope that you will be present for future events. Casey has a little short 5-minute survey for you to record what your feelings are about this event, and please do consider filling it out. Thank you very much, and have a good weekend.
Thank you, Herb. And thanks, Eileen.
Thanks everybody for coming.
Yeah.
Thanks to the speakers and all the organizers. Well done.
Thanks, everyone. That was great.
And organizers, I sent out a Zoom for us to join for just the postmortem. So if you have time, you can join. If you don't, no worries.
See you in a minute.
Maybe we have another word than post-mortem.
I like that word. You learn a lot.
Yeah.
And then I think we'll just get the recording from Tanya.
Right.
Thanks so much for your help too, getting us organized.